All right, so in section 7, we're going to be talking about redistribution, right? The ability for us to take routing information or routes from one routing process and move them into another routing process, maybe from OSPF to EIGRP, or maybe some static routes that we're sending into EIGRP or OSPF and so on. When it comes to redistribution, we need to understand a couple of basic rules, right? What are the seed metrics that are applied when we do the redistribution? A seed metric is basically a metric that, because the metrics between the routing protocols are not common, right? You can't really compare hop count to cost, or you can't compare the composite metric from EIGRP to the OSPF cost metric. So we have to plant a seed metric when we do the redistribution that provides us the ability to identify what that initial metric is for the routes that are being injected. So you need to know about that. We also need to know about what the basic restrictions are for redistribution and what the potential downfalls are for redistribution, especially if you're doing two-way multi-point redistribution where you have multiple redistribution points in the network, and there's a possibility that you would create a loop in the network if you did that redistribution without some specific filtering and so on. So in this section, we're really just going to talk about, number one, why do we need redistribution? Why is it important? We're going to talk about what are some of the basic, what's the basic syntax to define redistribution. We'll talk about route redistribution between two different routing protocols. What are the default metrics for redistributing routes? Is it infinite? Is it a cost of 20? Those kinds of things. With OSPF, we're going to talk about the difference between an E1 route and an E2 route for those external routes that are getting sent into OSPF. And then we'll take a look at some of the different types of redistribution. You know, for example, is it a single point one-way redistribution? Is it single point multi or bidirectional redistribution? Are we going to be doing mutual two-way redistribution on two different routers? And we need to talk about, of course, what the problems with that are. And then we'll take a look at route filtering. When we're doing redistribution, what would be the need to apply route filtering? Specifically, what is a distribute list? What is a prefix list? What are route maps? We're going to talk about how those work in regard to redistribution. Of course, prefix lists and route maps we can also use for policy-based routing, which we'll be talking about later on. And then we're going to talk about the description of route maps. How do we use route maps to control routing updates in our topology? And what are some of the non-default values for administrative distance that we can use to manipulate how routes are interpreted and how routing information sources are interpreted as we do this redistribution as well. We'll also take a look at route tags, and then we'll take a look at some of the caveats for redistribution as well as part of our discussion here. So why do we need redistribution? Why is it important? Well, typically you try not to run multiple routing protocols at the same time. But there are scenarios where you might have to do that. Maybe you're merged with another company, and that company happens to run one routing protocol and you're running a different routing protocol. So you're in the process of doing a migration, but before that, you need to integrate the two networks together. So you might have to do redistribution for that. Maybe you're connecting to a different organization. Maybe it's an extranet, and they run one protocol and you run the other. And you do want to have an exchange of information, but either organization is not really going to change how they decide to do their routing. So for that purpose, you might see that. Or if you have application-specific protocol support that you need. Maybe there's a particular feature within a routing protocol, or maybe a particular concept within a routing protocol that requires you to use that particular routing protocol in a particular environment, but you don't want to necessarily migrate to that protocol completely, or you might have a mixed vendor environment. Mixed vendor environment would be like if you want to, say for example, run EIGRP in an environment where you have a Juniper router or some other third-party router outside of Cisco, and you can't run EIGRP, so you need to run OSPF in that particular case. So there are many reasons. I would say the general rule, though, is to try and kind of avoid using multiple routing protocols. There are just some cases where you just can't get away from it, so you have to do that. All right? So route redistribution, really by definition, is simply the exchange of routing information between different routing protocols. And that's really all it is. Or it doesn't even have to be a routing protocol. It could be a different routing information source as well, like a static route or a connected route that you're sending into a different routing protocol. So there may be different reasons to have this redistribution, but again, it doesn't really matter what the reason is. The bottom line is you still need to understand what the impact of that is, and of course we need to talk about also what the need is for, or the method that we use to do the redistribution. What could be a route information source in the redistribution process? It could be another routing protocol, so OSPF to EIGRP or OSPF to BGP. It could be static routes, so maybe we do a redistribute static for the purposes of injecting maybe a default route or something like that, or maybe some other static route that we don't want to be part of our routing protocol, or it could be connected routes, redistribute connected. So any kind of route source is fine. If it's a route source that can exist in our routing information base, it is a route that we can put into our routing environment. All right. Now, here's the really important concept, and we see it listed at the bottom of the screen here. You can only inject routes into another routing process if those routes are valid. In other words, we would never redistribute routes into another routing protocol that doesn't already exist in our global routing table. That means to say that basically, look, we can only inject routes that we're using. And that's a mechanism that's built in, or a fail-safe that's built in to protect us from injecting routes that don't exist in the topology, maybe potentially creating loops in the network or false routing information in the network and so on. All right, so that's a kind of an important concept in this regard. We only redistribute routes that we have in our routing table. All right, and we'll talk more about that as we get into the discussion of the concept of summarization and redistributing maybe kind of more generic routes rather than redistributing more specific routes and so on. But it's all about being able to redistribute what exists in our routing table. So here we see kind of a diagram that represents where redistribution takes place. Router A happens to be running OSPF and EIGRP in this particular case. We define that as the boundary router. And then we set up a redistribution policy on router A that says take the routes from EIGRP, send them into OSPF, take the routes from OSPF and send them into EIGRP. You'll notice here too that as the routes get redistributed, they get identified differently than what we would typically see for an internal route. DEX are external routes, meaning these are routes that are outside of the EIGRP autonomous system. And in the case of OSPF, we have OE2. We can see that over there for the 192.168.5.0 subnet, and that's an external type 2 route. Now, we don't really have an option with regard to how routes show up in EIGRP based on the denomination, if you will. But for OSPF, we can send a route in as an OE1, we can send it in as an OE2, we could send it in as an ON1, we can send it in as an ON2, and we talked about that in the previous section when we were talking about OSPF and type 5 LSAs versus type 7 LSAs and so on. All right? So within the autonomous system, we know that we have complete visibility or knowledge about the network. And then this boundary router is basically participating in both of those autonomous systems. So we go into the routing process and we redistribute the routes, which allows the routing protocol to advertise the routes that weren't learned within that protocol but learned in the other protocol. And in this case, it's OSPF to EIGRP and vice versa. This is what we refer to as single point mutual redistribution. We have one router that's acting as the boundary. It's taking the EIGRP routes and sending them into OSPF, and it's taking the OSPF routes and sending them into EIGRP. But there are some rules here, right? For example, when I redistribute from EIGRP into OSPF, there's a default seed metric. It happens to be a cost of 20. We don't see that listed in the diagram here. But when I redistribute from OSPF into EIGRP, the default seed metric is infinite. So that's another thing that you need to be familiar with is when I do this redistribution, how is the metric affected? Because the reality is you cannot take a metric from one routing protocol, which is calculated completely differently, and somehow interpret how that metric is supposed to show up in the other routing protocol. For example, you look at the metric for EIGRP, right? It's a composite metric, 5K values, you have bandwidth and delay, K1, K2, K3, K4, K5, and there's this complex formula that allows us to calculate the metric for EIGRP. And it gets even more complicated when you're running EIGRP in address family mode, because now we have the wide metrics and we have very, very large metric values. But the metric for OSPF is cost, right? And cost is a very simple metric, 10 to the power of 8 divided by the link bandwidth in bits per second. So the numbers that are going to be calculated for the metrics themselves just do not correlate. So whenever we're doing redistribution, we don't automatically translate those metric values to go from one routing protocol to the other. So what we have to do is we have to establish what we call a seed metric. A seed metric is something that you define as an administrator, or it's defined by default in the case of OSPF, that plants the seed. And that's why it's called the seed metric, that plants the seed of what that initial metric is going to be for the route that's being redistributed. In this example here, we're running named mode EIGRP, or what we call address family mode EIGRP. And under the IPv4 unicast address family for Autonomous System 100, we are redistributing OSPF, OSPF v3, which is essentially OSPF for named mode as well, Autonomous System number, or process ID 10, excuse me, and we're applying this default seed metric, all right? So we're taking routes out of OSPF and we're sending them into EIGRP. And by applying this default metric, we're saying, okay, this is the bandwidth, this is the delay, this is the reliability, this is the load, and this is the MTU. These are typically the 5 values that we specify when we're talking about defining a metric for EIGRP. Even though MTU isn't specifically used in the formula, it is used as a tiebreaker in the case of load balancing and so on, where we have maybe potentially too many paths to load balance over and so on. All right? Now there's a couple ways you can do this. You can apply this seed metric. You can do it through the default metric command, meaning that it doesn't matter what redistribution I have. It doesn't matter if it's redistribute static, redistribute connected, redistribute OSPF. Every redistribution process is going to have that same default seed metric. Does that make sense? Or I can apply the metric directly on the redistribution command. So I could come in here and I could say redistribute OSPF, process 10, metric. At the end of this line, I would put the word metric, and then I could specify the metric, and that metric would only apply to the OSPF redistribution process. The other way you could do it is you could do it with route maps. You could create a route map that sets metrics matches particular routes that are being redistributed. So maybe we don't want to treat every single route the same. Maybe there's 100 routes that are being injected from OSPF, and half of those routes I want to be E1 and the other half I want to be E2. Half of them I want to have a certain metric. We're going into EIGRP, so E1 and E2 wouldn't apply in this case. But maybe I want to apply a different metric to half of those routes in the case of EIGRP. So for that reason, I might want to create a route map, and then in that route map I match through an access list or a prefix list, I match certain networks, and then I can set the metric individually. I'll demonstrate that as part of one of our discussions a little bit later on, as we go through the process. So the default metric command, which kind of applies to the entire routing process, it basically establishes that seed metric for any routes that are redistributed into that routing protocol. But again, the metric can be applied as part of the redistribution command with the metric option, or by applying some sort of route map where you can set that initial seed metric. Now, it's really, really important to understand this. There are some defaults. The default seed metric for redistributed routes will depend on the routing protocol that you're redistributing into. So for distance vector protocols like RIP and EIGRP, the default seed metric is infinite. So if you are redistributing, if I didn't put this default metric command, if I did not put this default metric command, the redistribution command would still be valid, but none of the routes would come into EIGRP because, well, they would come into EIGRP, but they would come into EIGRP with an infinite metric, meaning that the routes would be considered unreachable. All right? So when you're redistributing into RIP or you're redistributing into EIGRP, the metric is going to be marked as infinite unless you specify specifically what that seed metric is going to be. How did I come up with these numbers? It's somewhat arbitrary, right? We may be basing these numbers on some sort of traffic engineering concept that we're trying to implement within the routing protocol. We may want these metrics to kind of look like a specific number. Maybe we want these routes to be less preferred or more preferred over other routes that we were learning in our topology. So there's no golden rule as to what these values should be. And if it's a single point redistribution, it doesn't really matter what the number is. It's kind of irrelevant. So you can kind of really just pick arbitrary values. The 1500 is the bandwidth, and that's in kilobits per second. The 100 is the delay, which is in microseconds. The 255 is the reliability, which is not really normally part of the metric anyway in EIGRP. Reliability, 255 is the most reliable, and 0 would be the least reliable. Load is 1. That's an 8-bit value as well, so that goes from 1 to 255. And 1 is the least loaded. But again, it's not really part of the metric in EIGRP, and the MTU, again, is really there as a tiebreaker in the case we have too many paths that we're trying to load balance over or something like that. All right? So the metric for RIP and EIGRP is infinite. There is an exception to that rule. If you're redistributing static routes or you're redistributing routes between two different EIGRP autonomous systems. So from EIGRP AS100 to EIGRP AS200, because they're both EIGRP, the metrics are compatible, so we can actually take the metrics from the original route and carry them over into the new routing process. Also, if you're redistributing from connected routes, or connected interfaces, I should say. If I say redistribute connected, for example, I don't have to specify a seed metric because the connected interface has a bandwidth, it has a delay, it has a reliability, it has a load. When you run show interface, you can see those values. So EIGRP will automatically use those values. Same thing with a static route. Static routes point to a next hop. which is always going to be associated to an exit interface, and that exit interface has bandwidth, delay, reliability, load. That's part of the interface itself. So we can use those values as the seed metric when we're redistributing into EIGRP. In OSPF, if I was to redistribute into OSPF, there are some defaults. First of all, the routes would come in as an E2, external type 2, which means that the seed metric would not be modified as I move through the OSPF domain. And the default cost is going to be a cost of 20. Okay? The only exception to that one is if you're redistributing BGP. If you redistribute BGP into OSPF, it's going to come in as an E2, but the default seed metric is going to be a 1, not a 20. All right? And then BGP is kind of interesting. If you're redistributing into BGP, because BGP doesn't really use traditional metrics, it uses path vector attributes to make routing decisions. We do maintain the IGP metric, but it goes into the med value or the metric value for BGP. So in the case of BGP, we don't really use metrics per se, so it's not as critical. You don't have to specify a default seed metric and so on. All right. So what we're going to do is we're going to kind of move into our first discovery of this section, Discovery 11, where we're going to implement a routing protocol redistribution. And we'll see some more of the, the syntax, and we'll see some more of the rules, and I'll kind of show you, some additional things that we just didn't cover in this basic introduction. All right. All right, so our first discovery of this section here is discovery number 11. We're going to be doing routing protocol redistribution. And basically throughout this discovery, we're going to learn how to perform some basic redistribution configuration tasks. We're going to be redistributing OSPF into EIGRP and EIGRP into OSPF for both protocols, IPv4 and IPv6. We're going to modify the metric type for the EIGRP routes that are being redistributed into OSPF. Remember, the default is E2, so we're going to modify that. In this particular topology, R1, R3, and R4 are already configured with OSPF v3 for both IPv4 and IPv6 using that address family configuration that we learned about in our OSPF section. And R1 or R2 are configured with EIGRP named mode. Again, address family mode for IPv4 and IPv6. So all the devices are already kind of prepared with their configuration. Our task is really just the redistribution piece. Set up redistribution from OSPF into EIGRP, and then configure redistribution from EIGRP into OSPF. So we can see the topology here. We have OSPF v3 process ID number 10. On the left, we've got a bunch of loopback interfaces in the v6 and v4 space, 21, 22, 23, 24, and DB8, 01, 02, 03, 04 for IPv6. Plus we got some physical links as well, and another loopback sitting behind router 3. And then on the right side, we have our EIGRP address family configuration with AS100 and AS200. And again, loopbacks 11, 12, 13, and 14, and 10, 11, 10, 12, 10, 13, 10, 14. R1, obviously in this particular case, is going to be the router that we're going to be doing our redistribution on. All right, all the routers have their basic configurations in place, host names, IP addresses, and R1, R3, and R4 are already configured with IPv4 and IPv6 address families for OSPF, as I mentioned before, and EIGRP named mode on R1 and R2 as well. All right. So our first task, well, for me normally, the first thing that I like to do to make sure, before I even start configuring redistribution, the very first thing I like to do is I like to verify that the routes exist in the border router, in the router that we're going to be doing redistribution on. Because again, Doesn't matter if you configure redistribution correctly. If the routes don't exist in the global routing table, the global RIB, they're not going to get redistributed. So before I even jump into redistribution, I want to do a show IP route. I want to make sure that we have the routes from OSPF and from EIGRP. And we can already see we're missing routes from EIGRP. It looks like we've got, for the OSPF side, we should have 21, 22, 23, and 24, and we do. And then on the V6 side, well, we should also have 11 as well. And we see 11 here. The 12 network is connected. And then on the V6 side, we should see the 01, 02, 03, and 04. There's 01, 02, 03, and 04. And we should also see 0192, which is the loopback on router 3. So we see that here. It looks like we're also getting a 05. That is the serial link between router 3 and router 4, so that's good. So it looks like OSPF is working fine. But the problem is I'm not getting any of those EIGRP routes. So the first thing I'm going to do is I'm going to do a show IP EIGRP neighbor. And it looks like we're missing a neighbor relationship between router 1 and router 2. Now this wasn't supposed to be part of the exercise, but it does bring to light or bring to point that before you even start configuring redistribution, make sure that you have the routes in the router that's doing the redistribution, because you can go and configure redistribution and then you go into your OSPF domain and you don't see those OE2 routes and you're like, well, maybe I didn't do redistribution correctly, when in actuality the issue was with the routing process. So let's do a show run section EIGRP first and see if we have network 172.16.13. That is the link between R1 and R2. That's autonomous system number 1, so that's correct. In IPv6, we don't really need to enable the protocol. It's automatically enabled when the address family is configured, but it is AS200, so that's correct. So my next step would be to make sure that the interface is up and running. So show IP interface brief, and it should be Ethernet 1.0, the 13.1 subnet. I'm going to do a ping to 172.16.13.2, which should be router 2. So it looks like we may just have a connectivity problem between router 1 and router 2. So let's go to router 2, show IP interface brief. 13.2 is there, but it looks as though it might be the wrong interface. Let's go back to our topology diagram. It should be Ethernet 1.1, not Ethernet 1.0. So it looks like a misconfiguration. There's a couple ways I can fix this. I can just change the cable, or I can do this. Let's configure it to the right interface. So I'm going to do a show run interface Ethernet 1.0, and I'm going to do a config T, and I'm going to do a default interface Ethernet 1.0. Default interface Ethernet 1.0. So that's going to take the config off of Ethernet 1.0, and then I can just, go into interface Ethernet 1.1 and paste that configuration in. Default interface just clears off the config from the interface. You do that in global config mode, and then you can paste in the config for Ethernet 1.1. I still need to turn on the interface, Ethernet 1.1, no shut, and hopefully we'll get our adjacencies. Yep, there we go. We got our adjacencies. So that was the issue with that configuration. All right. So now if we go back to router 1, now that we fixed that issue, we can see that we have our EIGRP routes. It should be 11, 12, 13, and 14. And if I do a show IPv6 route, I should see the 10, 11, 10, 12, 10, 13, 10, 14. And here's the 10, 11, 10, 12, 10, 13, 10, 14. So again, it's important that you kind of check that first. Make sure that you have a stable environment. Make sure that you have all the routes that you expect to see before you actually start going in and doing the redistribution. All right? So the first step that we're going to do is we're going to configure redistribution from OSPF into EIGRP. So on router 1, because that's the router that's participating in both routing processes, we're going to take the routes from OSPF v3 and put them into EIGRP AS100. And we need to specify the seed metric, again, because when we go from any routing protocol into EIGRP, the default seed metric is infinite. So we're going to go to config T. We're going to say router EIGRP Cisco. That's the name of our routing process. IPv4 unicast, IPv4 unicast autonomous system number 100. And we're going to go into the topology base in this case, topology base. Because again, we are modifying what's going into the EIGRP topology database. Anything that affects the topology database is going to be configured under topology base mode. And we're going to say redistribute OSPF v3, process 10, and we're going to specify the metric. Now again, the metric here doesn't really matter because we only have one place that we're doing redistribution. But when you're specifying the metric, it is bandwidth, which we specified as 1500 kilobits per second. It's delay in tens of microseconds. So we put in a delay of 1,000 microseconds, which is 100 tens of microseconds. Reliability, 255 is really just the maximum number, the best value. Load, 1 is the least load. And then finally MTU, which is 1500. All right. And by the way, the reliability and load and MTU numbers are almost always typically going to be those values because, again, they're not really part of the metric calculation. They're certainly part of the formula with regard to reliability and load, but because of the K values, which you shouldn't change, they're not really used in the calculation. All right, so in the case of EIGRP, we're using named mode, so the redistribution command is entered under the address family mode configuration, and it allows us to redistribute the OSPF routes from the OSPF routing domain into the EIGRP routing domain. So whenever we do redistribution, let me do a quick show run, pipe section router. Whenever we're doing redistribution, we're always specifying the source protocol, where the routes are coming from. All right, so redistribute OSPF v3 is the source, and the destination is the named mode, specifically autonomous system number 100 in this particular case. That's our target protocol in this particular case. All right. Now there are other options. You know, you could specify, a route map if you wanted to use a route map to manipulate how redistribution takes place, and then you would reference the route map name. But outside of that, not really a whole lot of other options. The metric obviously allows us to specify the seed metric. You've got the bandwidth metric, and that can be anywhere from 1 to 4.29 billion. It's a little bit larger than that. The delay value is also anywhere from 1 to 4.29 billion. Reliability is anywhere from 0 to 255, where 255 basically says that it's 100% reliable. The load metric is 1 to 255, and 255 is 100% load. So again, those numbers don't really matter that much because in our particular case, we're not using those as part of our default metric. The MTU bytes that we specified, 1500 is pretty typical. That number can go anywhere from 128 to 4,352, but 1500 is pretty common. So looking at our topology then, if we go back to our topology, we should now see on router 2 those DEX routes. Because remember, we haven't done redistribution from EIGRP into OSPF yet, just from OSPF into EIGRP. So let's go into router 2 and let's take a look at show IP route, EIGRP, and we should see the 11, the 12, the 21, the 22, the 23, and the 24 subnets. These are all the subnets that are coming from OSPF. Notice, and the 11 as well. Notice the administrative distance. For DEX routes, the default administrative distance is 170. Internal routes, which are our D routes, are EIGRP internal routes, those have an administrative distance of 90. This actually comes into play, or could potentially come into play later on, if we're doing mutual redistribution, 2-point mutual redistribution. We may see an example of that a little bit later on. All right? So now let's go ahead. We did our V4 redistribution. Now we're going to go back to router 1, and we're going to configure redistribution from OSPF v3 into EIGRP 200, which is our address family for IPv6. All right? Now, interestingly enough, when we do this, I want to show you something that's kind of unique. So let's go to address family, IPv6 unicast, autonomous system number 200. All right? Again, we're going to go into our topology base, and we're basically going to use the same command. Redistribute OSPF 10, metric 1500, and again, going over to router 3, show run section router. Just to confirm, we're running OSPF v3 process 10. Of course, you want to make sure that you're selecting the right process when you're doing the redistribution. So we're going to basically put in the same metric. The metrics are calculated the same way in IPv6 as they are in IPv4. So we're just going to do our redistribution. All right. Now there is something interesting here, because if you look at router 2's routing table, actually you look at the topology diagram first. Let's look at the topology diagram. The 12 subnet, which is the link between router 1 and router 3, you will notice that that 12 subnet shows up in IPv4, which makes sense, right? It is an OSPF network, so it should be redistributed. But if I go back to router 2 and I do a show IPv6 route, again, we should see those DEX routes. Let's do EIGRP. All right, we do see the DEX routes. We see the 1, the 2, the 3, the 4, the 5, the 10, excuse me, not the 10, the 192. So the 1, the 2, the 3, the 4, the 5, and the 192, but I don't see the 10. In order for the connected route to router 1 is the router that's doing redistribution. In IPv6, we need to add the word include-connected in order for IPv6 to include the connected OSPF routes in the advertisements. All right? It is maybe something that we don't necessarily have to do. It is a transit link. But if you did want full convergence, you wanted that to show up, it's really up to you as the administrator if you're going to decide whether the connected subnets are going to be included. But with the include connected command, we're basically telling that target routing protocol to redistribute the routes that are learned by the source protocol, all the routes, as well as the connected interfaces, assuming that the source protocol is running on those connected interfaces. So I could come back to router 1 as an example and just hit my up arrow and say include connected. And then when I go back to router 2 and I look at my routing table, I should see that 10 subnet. And sure enough, here it is. Well, actually, 1, 2, 3, 4, 5, 192. Let's refresh it again. 1, 2, 3, 4, 5, 192 should be there. Well, this is a 10 network. but that is the network here. Well, that's interesting. Why is it showing up as a D route? It's showing up as a D route because R1 is running named mode. So in this particular case, this interface, Ethernet 1.1, is part of EIGRP. Because if you go back to router 1, this is kind of a limitation of named mode. And if I do a show run section router, you'll notice that I'm not really specifying in the IPv6 address family, I'm not really specifying which networks are included in the EIGRP process. So here's the v6 address family for EIGRP. And if I do a show run, we're not explicitly enabling EIGRP under the interface. So there is nothing to indicate that EIGRP should be running on the interface. All right. OSPF there is, but not for EIGRP. So what's happening is automatically this network is being included in EIGRP, which is why it's showing up as a D route. So there may be, we may have to do some, I'm not going to change it in this case. It's not going to affect our reachability, but that's why it's showing up as a D route in R2, because it's being advertised through EIGRP to R2 internally as opposed to externally. So it was already there. But in any event, you would still need the include connected if for some reason this was not part of EIGRP, but you wanted it to be part of the redistribution process. That include connected keyword is important. All right. All right. So also notice under the EIGRP IPv6 family, it's not possible to specify OSPF v3 as the source protocol for redistribution. You know, we're running OSPF v3, so we kind of get into this habit of everything is done with OSPF v3. In fact, if I do let me go back to router 1, and I do a show run pipe section router, we can see that in the redistribution process for IPv4, we redistribute OSPF v3.10. But in the redistribution process for IPv6, we just specify OSPF 10. All right. In the case of IPv6, it kind of automatically just assumes that it's OSPF v3 because it's part of IPv6. The default OSPF version for IPv6 is OSPF v3. All right. So we already looked at the routing table. We can all the routes were imported. We expected that. The only one that we really probably shouldn't have seen was that 10 route. But again, that's because of the address family configuration. All right, being that the IPv6 address family just kind of automatically includes all the interfaces. We could suppress that from happening, but again, it's not really that important in this particular case. It's not going to affect our reachability. All right. So that 10 network is just showing up as an EIGRP route. So now we're going to go the other direction. We're going to configure redistribution from EIGRP into OSPF. So on R1, just like always, that's where the router that's participating in both processes. We're going to go to router OSPF v3, and it's process 10. We're going to go into address family IPv4 unicast, oops, and we're going to redistribute EIGRP 100. We're not going to specify a default seed metric. We're not going to specify anything other than just saying redistribute. The default seed metric is going to be an E2 with a cost of 20. All right. Now, for using OSPF v2, if we were using OSPF v2, we have to include the subnets keyword. That's kind of another rule when you're redistributing out of EIGRP or out of RIP, basically out of distance vector. The subnets keyword has to be specified so that all the classless networks would be advertised. If I don't have that keyword, only the routes that exist in the routing table that have a default classful mask are going to be redistributed. All right? So that subnets keyword would normally be important, but because we're running OSPF v3, it's not necessary in this particular case. All right? So the next step, of course, would be to just make sure that we see those routes, at least for IPv4. So we're going to go to router 3 this time, because router 3 is in the OSPF domain, and we're going to do a show IP route, and in this case, OSPF v3. And sure enough, we see the routes. We see the 11, we see the 12, we see the 13, we see the 14, and we see the 13.0/24. All right? The 10.10.13 is different than the 172.16.13. Notice that the administrative distance for external routes in OSPF is the same. This is a value that we can modify independently of the other types of OSPF routes. We can actually change the administrative distance for internal OSPF routes, inter-area OSPF routes, and external routes independently. By default, all of those types of routes have the same administrative distance. Also notice they're coming in as OE2. We didn't specify that. That was not something we configured. And they have a default cost of 20, or a default seed metric of 20. All right? External LSAs always get marked in the routing table as an E, unless it's a type 7, which means it's going to get marked in the routing table as an N. Now you have external type 1 or you have external type 2. And the cost of the external route is going to change depending on the external route type that you have configured on the ASBR. All right, so you can have an E1 or you can have an E2. E2, of course, is the default. With an E2, the external cost of the E2 routes are fixed. They do not change as you move through the OSPF routing domain. And the default cost is 20, as we can see here. All right. Typically, we would only use this type of route on our ASBR if we only have one ASBR that's advertising the external routes into the autonomous system, which in our case is what we have. An OE1 route calculates the cost by adding whatever the initial seed metric is, that initial external cost, to the internal cost of the links that the packet crosses through within the OSPF domain. And in this case, we would typically use this type of external designation to avoid maybe suboptimal routing if we have multiple ASBRs that are advertising those external routes into our autonomous system. So in our case, we don't necessarily have to change it. We are going to change it just so I can show you how that looks, but we don't necessarily have to change it because we only have one ASBR. That ASBR happens to be router 1 in this particular case. So let's go back to router 1 and let's just go ahead and kind of change that. We're going to say redistribute EIGRP 100 and we're going to say metric type and just put in a 1. Very, very simple. So now if I go back to router 3, you can see that those are coming in as OE1 routes, and the cost of the link between router 1 and router 3 is being added to that initial seed metric. All right. Again, external routes can be sent in as E1 or E2. Router 1 still receives the same external routes. We didn't lose anything, but because they're E1, that internal cost of the links is being added to the cost of that initial seed metric. All right. So that's IPv4. Now let's go into our, back to router 1, and let's go into our address family. IPv6 unicast, and we're going to redistribute EIGRP. In this case, it's 200, and remember, we want to put that include connected. In this case, we actually do need it because the EIGRP connected route wasn't automatically sent into OSPF. OSPF v3 doesn't do that. We actually explicitly enable OSPF v3 on the interface. So because we didn't explicitly enable OSPF v3 on this Ethernet 1.0 interface, we use the include connected to make sure that 13 subnet is part of the process. Okay? So we're going to go back to router 3 and we're going to verify our routing information. Show IPv6 route, OSPF, and we should see them. There's the 13, there's the 11, 12, 13. This is DB8013. This is DB81013 and 1014. So the 013 is the Ethernet link, and then these are the loopbacks. So we are seeing all of the routes. And again, notice they're coming in as E2. The cost is 20. So just because we're running IPv6 doesn't mean that it's different. It's still the same. Okay? Of course, I would also want to make sure that the routes are making it over to router 4. Router 4 is kind of an internal router as well. Show IPv6 route OSPF. And we see the 013. Same seed metric, cost of 20 because it's an E2. 11, 12, 13, and 14 are there as well. All right. But what if we wanted to change the metric type? It's the same way. We do it the exact same way. We do metric type 1, go back to router 4, and we can see now those are coming in as OE1. All right, very, very simple concept. They come in as OE1. Obviously, if they're coming in as OE1 on router 4, that means they're going to be an OE1 on router 3. All right. All right. So that really kind of concludes our first discovery in this section. We got a little bit more lecture. We'll see you guys in the next section. All right. So when we talk about calculating the cost for those external routes, this is something we've already kind of talked about. The cost of that external route depends on how the route is sent into OSPF from the redistribution process. OE1, external cost of the link, it's added. OE2, the cost of the link does not get added. All right? So visually it looks something like this. If I have an OE1 or OE2 route that gets injected, the initial seed metric is still always going to be the same. It's still going to be a cost of 20. But then I have to add the cost of the links along the path if it's an OE1 route, which is a cost of 1, 1, and 1. So by the time I get to the destination, the cost is 23 for the OE1 route. All right? And again, it really just depends on what your overall objective is. Typically, if I have only one ASBR, I don't really care about changing it to an E1. If I have multiple ASBRs, though, I might consider changing it to an E1 just so I can distinguish the difference between the source of one of those external routes versus the other source of those external routes. Another important concept is to understand what kinds of redistribution we have. So the diagram, we see 4 different things here. 1-point redistribution basically means that there's only one redistribution point between 2 different routing protocols. Whether it's mutual or one-way, this is probably the safest way to do redistribution. There's very little concern about a loop being created in the network because, again, there's only 1 point of redistribution. So router 1 and router 2 in this particular case are very safe redistribution options. We can do it one way, we can do it 2 ways. It's very rare to see routes being redistributed one way because obviously when we communicate, we would like to communicate across the entire path. So we would most likely be doing 2-way redistribution, even if it is a single point or 1-point redistribution. But 1-point redistribution basically just means that routes from routing protocol A are being redistributed into routing protocol B, but not in the other direction. 2-way redistribution means that we're redistributing the protocols in both directions. All right. So one-way redistribution would require maybe the use of some other type of routing information source. Maybe it's a default route or a static route. Because if you redistribute routes from, say, routing protocol A into routing protocol B, or in this case, B into A, all those routing protocol A devices are going to be aware of all the routing information, but the devices in routing protocol B's domain are not really aware of all the information. They're only aware of what exists within their autonomous system. And then reachability for the destinations that are actually outside of routing protocol B would require the use of some sort of default routing or static routing. All right. This type of redistribution, both what we see on router 1 and router 2, is going to be completely safe because one-point redistribution only provides one exit and entrance point from one routing protocol to the other. So you cannot, there's no way to inadvertently create a routing loop in that particular case. If you look at the bottom two options, multi-point redistribution, that's where we're redistributing between two routing protocols, but it takes place on two or more devices that are both running the routing protocols. So I can do multi-point one-way redistribution, which is relatively safe, but the one that we have to concern ourselves with the most is multi-point two-way redistribution. And in this section here, we're going to talk about what are some of the potential issues by doing that two-way redistribution on multiple points. All right. Any kind of multi-point redistribution is likely to introduce routing loops. You have to be aware of that. And it has to do with primarily administrative distance values between the two protocols, or maybe incompatible metrics, and we're having to specify different seed metrics and so on. So we're going to focus our attention on what those potential problems could be, specifically when we talk about mutual redistribution. Two-way redistribution or mutual redistribution, you have to be really, really careful with the design. And we'll use things like route tags, we'll use filtering to make sure that we are applying the appropriate filtering to avoid those downfalls, those problems. All right? Obviously, during redistribution, we can also lose our metric information. And that typically happens, right? Now, you could maybe try to retain that metric information by using appropriate seed metrics in the redistribution process. But the reality is, it's never going to be perfect because we just simply don't have a good way or an easy way of representing one metric in another routing protocol. We kind of have to just pick what it's going to be. So to avoid problems with maybe some automatic loss of those metrics, we would statically assign our metrics that we're going to use to influence path selection and so on. All right? But in any event, this multi-point two-way redistribution can cause lots of issues, and it requires that you take a lot of consideration. All right? We know that, by the way, when we're redistributing from one routing protocol to another, the metrics are just simply not compatible, and metric information gets lost. So you have to really consider what type of seed metric you're going to apply in the redistribution process, and then you want to pretty much statically assign those metrics at the redistribution point. All right? What kind of problems could occur? Right? You could get suboptimal routing, for example. Maybe the total path cost is not considered. Only part of the path cost is considered, and that could result in suboptimal routing. Or you could have these kind of what we call self-sustained routing loops. Once we lose a route, it generates a routing loop, and so on. All right, so there are some general recommendations that we take into account when we're doing this redistribution. Maybe number one, we only insert routes that are internal from one protocol to another and vice versa. We don't want to reinsert routes that were learned from another process. Route tagging is really important as well. It's a very easy way to identify and filter out routes that have already been redistributed. I'm going to show you guys how to do a route tag later on. We tag the routes, and then based on that tag, we can identify whether or not those routes should be redistributed or not. So I would tag routes, say, for example, from routing protocol B, give them a tag of 20, and then when I'm redistributing back, I say don't redistribute routes that have a tag of 20. A tag is like a little label that we apply to the routes themselves. All right? Sometimes we might want to propagate different metrics from protocol A to protocol B. That's not going to prevent routing loops, but it might give us more visibility on the best or most optimal path. And then also we can avoid routing loops by using some sort of default routing, because longest match routing is still going to apply in our routing protocols, and a default route would be the last thing that we choose. Okay? So what you're seeing in this particular diagram, we have two-way multi-point redistribution. All right, but the problem here is that the cost of the internal links in routing protocol A are different from the costs of the links in routing protocol B. You see we have in routing protocol A a 10 meg link and a 200 meg link, and routing protocol B we have a 200 meg link and a 100 meg link. Now it's obvious in this particular diagram that the best path between router 1 and router 4 is through router 3, right? That's a 100 meg link plus a 200 meg link, as opposed to the 200 plus 10 meg link, all right? But during redistribution, especially redistributing from protocol A to protocol B, the metric gets lost, and R1 is going to send the packet towards R4 through R2, all right? And that's primarily because this metric, local metric, is better than this metric. Now, how could I fix that problem? When I do the redistribution from protocol A into protocol B at this point, I inject it with a much higher seed metric than when I redistribute protocol A into protocol B from this point. That's what I was talking about when we talk about statically assigning a metric. If I was just to allow kind of apply the same metric in both cases, regardless of whatever the source protocol is and the target protocol is, if I apply the same metric, the same seed metric, then it's really just these links here that are used to decide the appropriate path. So this is a suboptimal routing example, but it's a pretty easy example or a pretty easy problem to overcome in this particular case. We just have to make sure that when we present the seed metric that we make the path through R2 look less inviting than the path through R4 or through R3. All right, so another example we see here is multi-point two-way redistribution, but in this particular case we're introducing a routing loop. All right, so router 1 and router 2 are connected via RIP up at the top here, and they both have learned about the 10.2.0.0 subnet through the RIP process, okay? But both of these routers are also running OSPF, and they learn about the 10.3.0.0 subnet through the OSPF process. So far, so good. That sounds about right. That's what should happen in this particular case. All right, but the problem is that network 2 gets redistributed from RIP into OSPF by both of these routers. All right, and then the same would apply, of course, for network 3. Network 3 is going to get redistributed into RIP by both of these routers. So far that doesn't really sound like much of a problem, does it? Sounds like that's exactly what we're trying to get. But now we have to consider administrative distance. The administrative distance of OSPF is 110. The administrative distance of RIP is 120. All right? So in this particular case, a routing loop potentially could occur. Definitely suboptimal routing could occur. All right? So let's take a look at from the perspective of the 10.2.0.0 subnet. All right? Now we know that this network is being learned through RIP because it's just part of that network. R4 first sees it with a hop count of 5. That's just what's documented here, right? We see a hop count of 5. R4 then propagates this route to R3 and R2. All right? That's going to end up having a hop count of 6 because we're now adding ourselves to the path. R3 then propagates the route to router 1, and by that time we have a hop count of 7. So it's a hop count of 6 here, a hop count of 6 here, and a hop count of 7 here. All right? Now, R1 has to make a choice, right? It has to route to the 10.2 network. Now, if I use the RIP route, it's going to have an administrative distance of 120. All right? But remember, we are redistributing that RIP route into OSPF from router 2. So R1 is actually learning about the 10.2 subnet from router 2 as well via OSPF. It's an external route. It's an OE2 route or OE1 or whatever, but it's an external route. But the problem is OSPF has an administrative distance of 110 by default. So because OSPF has a better AD, R1 is going to choose that path to get up to the 10.2 network as opposed to using the native RIP route, which has an administrative distance of 120. Also, because R1 sees that as a better path, it's going to redistribute that route back to RIP with whatever metric is set in the RIP command. So what if I happen to set a static metric of 3, right? Sorry about that. What if I have to, in my redistribution process, I used a static metric of 3 in the redistribute command. So R3 then starts preferring the path through R1, then R2, then R4 to reach the 10.2 network. Because the hop count in this case was advertised as by R1 as a 3. All right? And then the hop count advertised by R4 is 6 in this particular case. So now we have suboptimal routing, but it gets worse than that. Because R3 prefers the path to R1, it now advertises the same route to R4 with a hop count of 4. Now R4 has a choice of the route from R3 that has a hop count of 4, or the true path, the one that it was originally learned with a hop count of 5. So it's going to select the path through R3. It's then going to advertise that path to R2, which basically means, I know it's confusing, there's a lot of different directions going here, but basically we've created a routing loop. We're going to go from R4 to R2 to R1, then back to R3, then back to R4. All right? And they're just going to bounce around, and network 2.0 or 10.2.0.0 is going to become unreachable. Now we could have solved this problem a couple of different ways. Make sure that the seed metric in the redistribution process doesn't present a more optimal path or doesn't present a more viable path. That's number one. Number two, we could actually change the administrative distance of external routes in OSPF. We could say, you know what, let's make the AD of those external routes in OSPF, let's make that AD 130 or 125 or something like that. Something that's higher than RIP so that the OSPF route wouldn't be preferred. But it's a little bit more complicated than that, right? We don't see bandwidths listed here. It may be that these links present a better path because maybe these links are gigabit links and these links are fast Ethernet links. So from router 1's perspective, I should prefer to use this path. It gets a little complicated in that sense because now you have to start considering, okay, how is the router going to react to the information that it's being presented with? Routers make basic routing decisions. They're going to make a decision based on metric. They're going to make a decision based on AD. They're going to make a decision based on longest prefix. You know, the standard routing protocol decisions that routers make. So you have to think like the router. And you have to engineer or design your redistribution method and to reflect what you know as an administrator is the best option for the protocol. So it's not just a matter of just going in and saying, okay, redistribute A to B and redistribute B to A and call it a day. You really have to think about the impact of that redistribution process in your environment. Okay? So we've already seen kind of different scenarios where we have to manipulate the redistribution process. Maybe the metrics need to be changed. Maybe there are some networks that we want to redistribute and some networks that we don't want to redistribute. Or there could be other reasons. Maybe we want to redistribute network ABC a different way than XYZ. And so we have a lot of options. In the case of Cisco iOS, we have to classify the routes that we're going to be manipulating. We can do that with an access list or a prefix list. We'll talk about the differences between prefix lists and access lists as part of our discussion here. We can use distribute lists. We can use route maps, a very, very powerful tool. Route maps are an extremely powerful tool for us to be able to kind of manipulate how redistribution occurs. So what you're seeing in this particular example is that maybe we only want some of the routes to be redistributed. In the redistribution process, it's not really distinctive. Not by default. It doesn't really distinguish between one network or the other. We're redistributing from a source protocol to a destination protocol, and that's it. But by applying a prefix list filter in conjunction with a distribute list or a route map, we can identify, okay, I want the 10.0.1.0 subnet to go in, and I want the 10.0.2.0 subnet to go in, but I don't want 101 and 102 to go in. Okay? That's certainly an option. We could even get more specific. I could say I want 10.0.1.0 to go in as an OE1, and I want 10.0.2.0 to go in as an OE2. Or I want the seed metric for 1.0 to be different than the seed metric for 2.0. And so it's virtually limitless as to what we can do in the redistribution process. There's not really, we have a whole bunch of flexibility. You'll find that route maps provide us that flexibility with our different set conditions and our different match conditions. Okay? So here's an example, is we have an access list 7, which is just a standard access list. By the way, when you're matching routes in an access list, it's always going to be a standard ACL because we're matching on a source. These are not packets that are being routed. This is information that's being sent from a routing table. So it is technically considered the source because it's the source of routing information in the routing table. So in this case, we've created a standard ACL, classic numbered ACL. We could use named as well. We don't have to use a numbered ACL in this case. And we're matching any route that starts with 10.10.11 and any route that starts with 10.10.12. Okay? Now the downside to an access list is that it doesn't provide us the ability to match on prefix length. So I don't have the option of saying any route that starts with 10.10.11 that has a subnet mask of /28. Or any network that starts with 10.10.12 that has a subnet mask of /27. We would have to use a prefix list for that. But if our goal is to just generally match networks, we don't care about the length of the prefix, an access list is a good way to do that. So we've created this access list, right? Access list 7 that matches 2 different networks. And these again are networks that exist in the routing table of router 3 from the EIGRP domain. I go into my OSPF process and I do my redistribution, right? I'm specifying my redistribution right here, but notice I am applying, and by the way, the same rules apply to redistribution whether you're applying a filter or not. These routes are going to be redistributed into OSPF v3 with as a type E2 and a default cost of 20. So that didn't change. We didn't apply a metric or metric type. And we didn't have to use the subnets keyword here again because this is OSPF v3. If this was OSPF v2, we would have to use the subnets keyword. All right? Remember, IPv6 is classless by nature. IPv4 started as a classful process. But now we've applied a distribute list. We're saying, I want to filter what's being redistributed. So the distribute list applies to what's being extracted from the source protocol based on access list 7. The direction implies the source protocol being EIGRP in this case. So basically the way I read this is I say, I'm applying a distribute list based on access list 7 for the routes that are coming out of EIGRP, specifically out of EIGRP autonomous system number 100. So what is permitted by the access list would be distributed, and because there's an implicit deny at the end of the access list, what is not explicitly permitted is going to be denied. Which means in this case, the 13 and 14 subnets would not get redistributed. Make sense? This is actually one way. We can actually use distribute lists in our peering relationships as well. We'll see that in one of our future sections here. Distribute lists can be used a couple of different ways. All right? Now, the access list itself does not affect traffic that's originated by the router. All right? So when we're applying one to an interface, it doesn't really have any effect on routing advertisements. So we can't really kind of use the access list in a sense of saying, let's apply it to the interface and then maybe apply it to the routing process, and it will somehow filter those routes. But when we link an access list to a distribute list, like we've done in this particular case, we're able to control those routing updates, and it doesn't matter what the source is or where the source is. All right, we still create the access list in global configuration mode, but then we reference that access list through the distribute list command, and then the access list, of course, based on its permit or deny statements, will identify what should be advertised or redistributed and what should be filtered in this particular case. All right, so we're applying this access list to the routing updates for that particular protocol. We can do it based on 3 different factors. The distribute list in this case is being applied from redistribution from another routing protocol. But like I said, later on in another section, we'll see where we can apply redistribution, or excuse me, a distribute list outside of redistribution, not related to redistribution, based on a relationship for an inbound or outbound interface. All right. So the idea here is that we're simply kind of filtering what's happening with the redistribution process. All right. So here's a couple of examples. This is really just the same example that we saw, right? But here's an example going the other direction. We've got router EIGRP Cisco. We're redistributing OSPF into EIGRP. There's our default seed metric. Otherwise, the routes would not work because they would have an infinite metric. And I'm saying, okay, I'm going to apply distribute list 7 out of OSPF. So what's coming out of OSPF and being sent into EIGRP? If I use the distribute list in command, that would never really apply to a redistribution process. The distribute list in command would be applied to like a routing relationship. Here's an example of that. So I go into router EIGRP Cisco, and I go into my address family for AS100, and I say distribute list 7 in serial 0. So what this is saying is that if I have a neighbor on the serial 0 interface, this is the only way this would apply. It doesn't apply to packets that are being routed. It only applies to information I'm learning from a routing process. So if I apply this distribute list to to, I'm applying this distributed list, I should say, to anything that I'm learning from my neighbor on serial 0. Does that make sense? So if my neighbor is advertising to me, I don't know, 20 or 30 different routes, whatever is permitted by access list 7 is what's going to go into my topology database. Anything that's denied by access list 7, I will not put into my topology database. So a distribute list is a really nice way to filter what you're learning from your neighbor. We understand that if I have a neighbor, if I get a neighbor from, or I have a neighbor relationship, in other words, I've formed an adjacency with another router, there is no restriction on what those routers share with each other, not by default. If you and I became neighbors, I would tell you everything I know, you would tell me everything you know. This distribute list option gives me a way of filtering that information, of saying, yes, you're telling me everything you know, but I'm only going to add to my topology database what's permitted by access list 7. It's a little bit different with OSPF, because in OSPF, the link state database has to match on all the routers in order for them to function. But so you cannot filter what goes into the link state database in OSPF, but you can filter what you're using. You can filter what you're using in OSPF. So that's, we'll probably see that, we'll definitely see that as part of our discussion later on when we get into route manipulation. All right. Another tool that we have at our disposal is a prefix list. Okay. Traditionally, we would always do filtering with an access list, and we would use distribute lists to apply those filters and so on. But there are a lot of issues with that. We cannot match on prefix length. In other words, and again, this is because we're matching routes. Routes always have a prefix length associated to them. An access list doesn't consider the subnet mask of the route. An access list only considers the route itself. Okay, so there's a limitation there. Access lists would have to also be evaluated sequentially for every prefix in the routing update. Meaning that if I have 1,000 routes, I have to process each one of those 1,000 entries against the access list, which can be CPU intensive, it can be memory intensive, and so on. All right? And extended access lists are cumbersome, although you typically wouldn't use extended access lists in a filtering process. You could, potentially. There are some use case scenarios for that, but typically it's standard access lists. So prefix lists were implemented to kind of address a lot of these particular concerns. Prefix lists are much better at processing information. They require more resources, or less CPU. But the most important piece is that a prefix list can match on prefix and prefix length. Now we will see later on some more details about prefix lists. So we're not going to see kind of all the details in this particular case. But later on in our route manipulation discussion, we'll have kind of a more detailed discussion about prefix lists because the way you write the prefix list will determine what its objective is, what its goal is. I'll try to discuss that a little bit here, even though it's not really part of the text here. All right, so here's an example of a prefix list. We create it in global configuration mode. We can do an IPv6 prefix list, or we can do an IP prefix list. This is the name. The prefix list is a sequence of commands, and this represents the name of the prefix list. And we can represent, or we can identify a permit or deny statement here. Now, there are many benefits of a prefix list, but again, the biggest benefit is the ability to filter on mask itself. So there are some operators that exist with prefix, what we call operands, less than or equal to, greater than or equal to, and so on. which we'll get into a little bit later on in our route manipulation section. In this particular case, when you do not see an operator, if you don't see an LE or a GE in the prefix list configuration, then when you see the address and the mask, it implies an exact match. Not only on the prefix itself, but the prefix length. So in this case, I am permitting network 10.10.11.0, but that route would have to be a 24-bit route. If it was 10.10.11.0/25, it would not be permitted by this rule. If it was 10.10.11.0/26, it would not be permitted by this rule. In other words, not only are we matching on the prefix itself, but we're doing a direct match on the prefix length. So if there was a 10.10.11.0 route with a 24-bit mask in EIGRP, it would be redistributed into OSPF. If there was a 10.10.11.0 route with a /25 mask in EIGRP, it would not be redistributed into OSPF. So prefix lists match on the address itself, plus they match on the prefix length. It's a very, very important concept. We can actually sequence our prefix list statements, so we can sort our statements if we need to. We can add statements to a specific location based on those sequence numbers or delete them. If we don't specify a sequence number, in this case the sequence number was not specified, then automatically default sequence numbers will be applied. It's kind of like when you create an access list these days, sequence numbers are applied automatically. Okay? So the router is going to match routing updates against the prefix list, depending on how it's referenced, right? It's probably going to be referenced to a route map. And we can specify, specific routes, okay? What we're not seeing here, though, is a way to manipulate the length of the mask. So I could say, for example, and we'll see this again later on, but I could say, for example, permit 10.10.11.0/24 and then add a GE28. A GE28. That changes the meaning of the prefix list completely. It means that the 24 bits that are represented here, I wish I could type it in as a PDF. Let me copy this real quick. And I'll just put it in Notepad so you can visually see what I'm referencing here. All right. So let's say I put a GE, which stands for greater than or equal to 28. By having this operator in the prefix list, it changes the meaning of the prefix list completely. Without this, it was an exact match. With this, the 24 bits no longer represents the subnet mask. The 24 bits represents how many bits in the address have to match for the route. So the way you read this is we say, I'm going to permit network 10.10.11 anything. I'm going to permit network 10.10.11 anything as long as it starts with 10.10.11 and the subnet mask of the route is 28 bits or more. So actually 10.10.11.0/24 would not match. See what I'm saying? 10.10.11.0/24 would not match. 10.10.11.0/28 would match. 10.10.11.0/29 would match, and so on. Right? So without the operator, it's an exact match. With the operator, the mask or the prefix notation here does not represent the mask anymore. So for example, if I say 0.0.0.0/0, this is a default route. So this particular prefix list is matching exactly the default route. But if I say GE32, what the 0 means now is I don't care what the address is. No bits have to match in the address. It could be a 1111, it could be a 10101010, doesn't matter, but it has to have a mask of 32 bits. So this is basically all host routes. If I said LE32, this is like a match any. Because again, I don't care what the bits are in the address, and it's any subnet mask less than or equal to 32. So this would match the default route, it would match any route. So when you have an operator, it changes completely how the prefix list is interpreted. If you don't have an operator, then it doesn't. So let's say, for example, let me think of one here. 127.0.0.0/1. All right? So in this case, it would actually have to be that route, which is not a real route. We would never see a route that looks like this. Okay? So this is really not even valid because this mask would never work with this prefix in a routing table. Not to mention that 127 is not even a valid route anyway. But what if I said GE16? So what does this match in this particular case? Right? Let me see if this is even valid. I kind of just made this up. The /1 would mean the first bit is fixed and the remaining bits, so really I should change this to a 128. Because 127, this wouldn't do anything because the first bit is 0 in a 127. The remaining bits are don't care, so the router would end up converting that to a 0. But if I do 128, that changes the meaning completely, right? The first bit has to match, and the first bit in this case is a 1. So this would match any route in class B and class C space that has a mask of 16 bits or more. Any route in class B or class C space with a mask greater than 16 or equal to 16. So 127, 126, 125, none of those routes would match because the first bit has to be a 1. Remember, 128 in binary is 1000000. This /1 means that we're matching against this bit. Make sense? We'll see more of this later on as we kind of continue on with our discussion, especially when we get into route manipulation, and we'll play with some more examples. But the main thing that I need you to understand is that depending on how the prefix list is written will determine what its meaning is. All right? If you don't have an operator, it's an exact match. If you do have an operator, it changes the meaning completely. It's just something to keep in mind. All right? So a prefix list can have, multiple lines. Each one of them has a permit or deny, and we would compare the information against those statements, and we would do that in a specific order. The iOS itself kind of optimizes the behavior of a prefix list, or at least the parsing of a prefix list. So it creates this tree structure, and when it evaluates routes against the prefix list, the matching conditions, the way we match the rules, is a lot more efficient than an access list. Access lists are always processed from the top down, regardless. So depending on how the access list is created or how long it is, could require a lot of resources. All right? When the router does evaluate routes against the prefix list, if the maybe the first rule that it's matching is a permit or deny, it will apply whatever that rule states. But just like any other security principle, access lists, route maps, etc., if none of the lines in the list match, there's always an implicit deny at the end. So unless there's an explicit permit, it's implied that there's a deny. All right? So the testing against a prefix list is always done using the prefixes themselves. We compare the number of bits in the prefix with the same number of bits in the network, and if they match, we continue with the examination of the number of bits that are set in the subnet mask, and so on. Basically what we talked about just a couple of minutes ago. All right? If you don't specify an exact range, or you don't specify a range, I should say, the mask has to match, and we talked about that. So take a look at an example here. So in this diagram, we have a prefix list called PFL2. They sequence the list here, but these sequence numbers would have been automatically created anyway, so you don't necessarily have to put the sequence numbers in there. We already know that this is going to be an exact match. So we're accomplishing the same goal that we saw with our access list example, but the only difference here is that not only are we matching on the address, but we're matching on the mask. All right? The end result is the same. So in this particular example, it wouldn't have mattered if we used the access list or we used the prefix list, because the end result is that the 13 and 14 subnets get denied, and 11 and 12 get permitted. And it's applied basically the same way. Distribute list, prefix. Make sure you use the prefix word, because if you take out the prefix word, it assumes that you're referencing a named access list. All right? So if I just said distribute list PFL2, it would assume that I have an access list on my router called PFL2, and it would reference that access list. All right? But as far as the actual effect, it's the same. It's the routes that are coming out of EIGRP going into OSPF, and we're applying this filter to that process. All right? And sure enough, if we were to go and look at our routing table, we would see that only the 11 and the 12 subnets would be routed, and then the rest of the subnets would be filtered because of the prefix list. Okay? All right, that brings us to our next discovery, Discovery 12, where we're going to manipulate redistribution. All right, so in Discovery 12, we're basically going to do basic redistribution, but we're going to do it with manipulation. All right, so we're going to kind of expand on what we did in the last discovery. We're going to configure a mutual redistribution between EIGRP and OSPF, just like we did before. We're going to filter it, though, using prefix lists and distribute lists. All right, and we're going to kind of identify how we can kind of selectively redistribute routes from one routing domain to the other. So in this topology, R1, R3, and R4, they're already configured with OSPF v3 for v6 and v4 using our address families, just like before. And R1 and R2 are configured with EIGRP, address families for IPv6 and IPv4 in named mode. EIGRP is using AS100 for both processes, v4 and v6, and OSPF v3 is using process ID 10. All right. All the devices are already configured. They have their basic configuration in place, host names, IP addresses, etc. So we have three major tasks that we're going to be completing in this discovery. Number one, two-way redistribution between OSPF and EIGRP. Distribute lists to filter redistribution for IPv4. And then finally, distribute lists to filter redistribution for IPv6. So you can see the topology here, OSPF area 0, R3 and R1, and OSPF area 2 between R3 and R4. And R2 is in EIGRP autonomous system number 100. All right. So just like we did the last time, the first thing I want to do is go into router 1 and verify that I have all of my routes. Show IP route, And I should see, from router 1's perspective, I should see 21, 22, 23, and 24, which I do, and 10, 10, 21, 22, 23, and 24. And then the loopbacks of 16, 21, 22, 23, and 24, which are right here, 21, 22, 23. Actually, just, I guess I misread that. That might be a typo in the diagram here. But we are seeing the prefixes, right? It's actually 2264 and 22128. We don't actually have a 23 and 24. So that's just a typo in the diagram. Which is fine, no big deal. All right, should be a 22 64 and a 22128. The bottom line though is that we do have the routes, okay? And then from the OSPF perspective, 41, 42, 43, and 44, and 172.16, 41, 42, 43, 44. There's the 41, 42, 43, 44, and then the 41, 42, 43, 44. I'll do the same thing for IPv6, show IPv6 route, and there's the 11, the 41, the 42, the 43, the 44. There's the 11, 41, 42, 43, 44. So we're seeing them in OSPF, and then we should see the 21, 22, 23, and 24 in IPv6 for EIGRP, which we are not seeing. Well, yeah, we should see them here. We're actually not seeing them in IPv6. So again, this is why we always check these things. It doesn't appear as though I'm seeing the D routes. I should see the D routes for these loopbacks 21, 22, 23, and 24. So what we need to do is go to router 2 and check the routing process. We know the interfaces are turned on because, so let me see if they have addresses. Show run interface loopback 21. They do have the addresses. Show run pipe section EIGRP. Let's see if address family IPv6 is set up. We are seeing Autonomous System 100, address family IPv6, which should automatically include those interfaces. Let's do this, show IPv6 EIGRP topology. So they're in there, 21, 22, 23, and 24 are in the topology. Let's go back to router 1, show IP EIGRP topology. Show IPv6, excuse me. We already verified v4. The EIGRP process is shut down on router 1. That's actually something that you can do with EIGRP for IPv6, is you can shut down the address family. So again, not supposed to be part of the lab exercise here, but it does point out the fact that before you start configuring redistribution, make sure that all of the regular routing is working. So config T, and then we're going to go into address family v6, and we're going to go no shutdown. That's just done under the address family. Okay, there's our adjacency. Now if I do a show IPv6 route, I should see those 4D routes, and I do now. Okay, so we verified the routing table, and we are now ready to start doing our redistribution. First thing we want to do is just kind of verify the initial state of the routing table, and we've done that. We've verified that the routes exist on router 1. We don't really need to verify that the routes exist on the other routers because router 1 is the central point of the topology. We can kind of assume that because the routes exist on router 1, that they exist on the other routers as well. So now we're ready to kind of go in and start doing our redistribution. We're going to start by doing two-way redistribution, OSPF and EIGRP for IPv4. So config T, router OSPF v3, 10, and we're going to say address family IPv4 unicast, and we're going to say redistribute EIGRP 100. All right. Now again, we're taking routes from EIGRP into OSPF, so a default seed metric is not required. They're going to come in as E2 with a cost of 20. I'm going to go into router EIGRP Cisco, and I'm going to say address family IPv4 unicast autonomous system 100 topology base again, and I'm going to say redistribute OSPF v3 10, and we'll put in our seed metric 1500, 100, 255, 1, 1500. Pretty typical values. All right. So the v4 EIGRP AS100 routes are going to be redistributed into OSPF process 10, and the IPv4 OSPF v3 routes are going to be redistributed into EIGRP, and then the metric values that are required for OSPF routes are specified for the OSPF routes to go into EIGRP. So our next step then in this case is then just to go and verify that it's done, right? So I'm going to go to router 2 to start with to make sure that I see the routes in router 2. Remember, we've only done v4 so far, so we're just going to verify v4. Show IP route EIGRP. And specifically, we're looking for those DEX routes, and sure enough, we see them. 41, 42, 43, and 44. Those are the 10s. And then the 172, 16, 11, 12, 41, 42, 43, 44, as well as the 11 subnet, which is the link between the other two routers. If you remember our topology here, that's this link here, this serial link. So it looks like everything worked. Router 2 has all of the routes coming from the OSPF domain into the EIGRP domain. Now let's verify on router 3. We could do this on router 3 or router 4. Router 3 is the closest to the redistribution point, so we'll do that. Let's go ahead and do a show IP route OSPF v3, and we see the E2 routes. We see the 21, 22, 23, 24, and we see the 172, 16, 13, 21, 22, 22, 64, and 22, 128. All right? So 11 external EIGRP routes. Those are the 8 loopback interfaces, R3's loopback interfaces, the links connected to R1 to R3, and R3 to R4. And the routing table on R3, 9 external routes in this case, which are all those OSPF routes that represent R2's 8 loopback interfaces. And then again, that link between R1 and R2. All right. We've also already verified the initial state of the routing table for IPv6. We did find a problem with that. The EIGRP process on router 1 was shut down. So we brought that up and our routes existed. So now we're going to go ahead and do our redistribution back on router 1 for IPv6 between OSPF and EIGRP. So far, we're just doing basic redistribution. We're not even applying a filter, which is also kind of a good point, right? Before you apply the filters, make sure the redistribution process is working. You implement and increments so that you can troubleshoot in increments. So we're kind of doing this in a progression. Now, if you're really comfortable with the process, you don't necessarily have to do it that way, but it is a good way to do it if you're learning. So address family, IPv4, unicast. We're going to redistribute EIGRP 100. That's our source protocol. But we're going to do the include connected. We talked about that. Why isn't it letting me do that? Actually, we're doing v6. I don't know why I typed v4. I just mentioned we were doing v6. There is no include connected for v4. So we're going to do our redistribute EIGRP 100 include connected. Then we're going to go to router EIGRP Cisco. We're going to go the other direction. address family IPv6, unicast, autonomous system number 100, topology base, because we're modifying the EIGRP topology table. If I could spell right, topology base, and we're going to redistribute OSPF. We don't need to type OSPF v3 in this case. It's kind of assumed because it is OSPF for IPv6. Include connected, and we need to specify our seed metric. 1500, 100, 255, 1, 1500. All right. So all of the EIGRP AS100 routes get redistributed into OSPF process 10, and all the OSPF v3 routes are redistributed into EIGRP. Again, we have to specify the seed metric for OSPF routes going into EIGRP, and the include connected option makes sure that those directly connected networks on R1 get redistributed as well. Same thing as we saw before. So now let's go to router 2, and let's make sure that we see those EX routes in IPv6. So we're going to do a show IPv6 route EIGRP, and we do see them. There's the 11, there's the 12, even though the 12 doesn't come in as EX, because again, in IPv6, the locally connected routes are automatically included with named mode. 41, 42, 43, 44, and the 192. Looks good. Looks like we have everything we need. Go back to router 3. We're going to be looking for the E2 routes. Show IPv6 route OSPF. There's the 13, the 21, the 22, the 23, and the 24. And these are our internal routes. So looks like we've got everything that we need to get. Routing table on router 2 shows us the 7 external EIGRP routes that represent R4's loopbacks, R3's interface, and the link between R1 and R3, and the link connecting R3 and R4. And the routing table in R3 shows us all those 5 external routes. Well, technically 4, right? Oh no, there's 5, yep. Excuse me, 5 external routes that represent the 4 loopbacks on R2. And then also the link between R1 and R2. All right, so we didn't do any filtering in this case. That's okay. We just wanted to make sure that the routing process was, the redistribution process was adequately configured to start with. Okay, so now what we want to do, and this is part of our task 2, we got 3 tasks in this lab. Task 2 is to configure a distribute list to filter redistribution for our IPv4 routes. And just pull up the diagram here. In R1, we want to configure redistribution from OSPF into EIGRP using a distribute list. We want an access list that filters out the routes 41, 42, 43, and 44. So we basically want to deny those and then permit everything else, and then apply the access list filter to the redistribution process. Now there's a couple ways that you can do this. You can apply it to the redistribution process, or you can apply it to the interface. All right. In our case, we have a relationship between R1 and R2. I want R1 to have the routes, which it already does because it's participating in OSPF, but I don't want those routes then to be advertised to R2. So in our case, we're not going to apply the distribute list to the redistribution process. We're going to apply the distribute list to this egress interface that goes from R1 to R2. So in R1's topology table for EIGRP, it will have those OSPF routes that are redistributed, but they will not be advertised to router 2. So let's go into router 1 first, and let's go ahead and create our access list. We could do this as a named access list, or we can do it as numbered. I prefer to use a named access list only because it provides me kind of a reference as to what's being applied. The book uses a numbered access list. I'm going to do a named access list in my case. IP access list standard. And we're going to give this a name out of EIGRP. Okay? Because, again, this is, in fact, let me do this. Let me do DST out of EIGRP, right? In other words, I'm referencing the routes that are being distributed out of EIGRP, all right? And I'm going to deny the 10.10.41.0 subnet. I'm going to deny 10.10.42.0, 0.0.1.255. That's going to include networks 42 and 43. You could put them in as separate lines if you want to. I'm trying to make mine as efficient as possible. And then I'm going to deny the 10.10.44.0, 0.0.0.255. All right? And then I have to do a permit any at the end because I want the other routes to be able to be sent out. Okay? Router EIGRP Cisco, address family IPv4, unicast, autonomous system number 100, topology base, because again, this is affecting the routing, and I'm going to say distribute list, and I'm going to reference my name, DST underscore out underscore EIGRP. And I'm going to say out of Ethernet 10. All right? Again, I'm applying the distribute list to information that's being sent to my peer out of this interface. All right? So just to confirm, do show IP EIGRP topology. I see all the routes that are redistributed. Redistributed, 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 redistributed. So router 1 is aware that those OSPF routes exist, and they are part of the EIGRP process. The question is, now, do they show up on router 2? So if I go to router 2, show IP route EIGRP, and sure enough, those networks are filtered. Let me see, make sure. You go back to router 1. I've got to keep my networks in order here. It's the 10 networks, right? Not the 172, but the 10 networks. And if I go to router 2, I don't see the 10 networks listed. If I do a show IP EIGRP topology, I also don't see those specific 10 networks listed. Okay? So the filter worked. This is kind of one way to do this. Now, it's not necessarily directly related to redistribution. The redistribution allowed the routes to go into router 1, but the distribute list allowed us to filter based on our EIGRP relationship, based on our adjacency, allowed us to filter what was going over to the peer. All right? So that is definitely something to consider in this particular case. There is something in the section here. Let me scroll down. This is all the stuff that we've already done as part of our exercise. Like I said, they used in the lab here, they used a standard ACL, right? Access list 5. I just used a named ACL. I think the named ACL is a little bit cleaner, honestly. All right. But there was one section here I wanted to pull up, the prefix list operators. I talked a little bit about this in our previous discussion. Prefix lists, again, are used for an exact match. All right. But with the operators, it changes the operation of the access list. The GE stands for greater than or equal to, and that can start at any number and go all the way up to 32 bits. LE is less than or equal to, which can start at a number and go down to whatever the length of the prefix itself is. And then GE and LE allows us to kind of specify a range. So you can see here in this example, IP prefix list any route. We talked about this in Notepad. This means I don't care what the bits are, and this is any subnet mask. Only the default route. Without the operator, it's an exact match. Here's an example, 192.168.00/16. So it's any prefix that starts with 192.168 because we're matching the first 16 bits. This 16 does not have anything to do with the subnet mask, although indirectly it kind of does. Not directly, but indirectly, because we're saying basically any network that starts with 192.168, but the mask has to be less than or equal to 20 bits. You would never have a 192.168 with a mask less than 16, but you could, we could say a /20, a /19, a /18, and so on. Oftentimes people will look at this and they'll say, well, that's basically a range from /16 to /20. But that's technically not what that means. It doesn't technically mean a range. Because how would this be a range, right? 16 to 18? No. It's match the first 16 bits, and then it's the subnet mask is greater than or equal to 18 bits. Okay? So prefix lists get configured to filter traffic based on the match of an exact prefix and the prefix length, or a match within a range with those GE and LE keywords, or those operators that we use to specify the range of the prefix length. All right? This gives us a much more flexible option, right? Prefix lists can process an exact match if they don't have the operators, or we can kind of use those operators to do more. All right? So what we're going to do now is we're going to edit our distribute list, or edit our redistribution process. Let me go back to my router here. We're going to go back to router 1, and we're going to apply this principle. When we're redistributing from EIGRP into OSPF, we're going to set up a prefix list to distribute routes that match 172.16.00/16, but with a 24-bit mask or less. Okay? Do we have any prefixes that are actually don't follow that rule? Let's see. Again, this is from EIGRP and OSPF. The diagram is not correct here, but these actually, I should just change this, because this was supposed to be a 22.64, and I can't remember what the mask was supposed to be. Let me go back to the documentation here real quick. Messed up my little diagram here. Yeah, there we go. Ah, there we go. Let me go back and check real quick. All right, so I fixed the diagram here. These are /26s. The reason that's important, obviously, is because we're going to be filtering those out, right? That's the whole point of the prefix list. If they were all /24s, it wouldn't make a difference. But they're actually /26s in the real world, all right? So let's go ahead and do that. We're going to go ahead and set up our prefix list, and then we are going to apply that prefix list. So let's go back to router 1 and config T, and we're going to say IP prefix list EIGRP to OSPF. So this is a prefix list that applies to routes coming from EIGRP and going to OSPF. That's just a name, but again, you kind of want to make that name somewhat relevant. 172.16, so it has to start with 172.16, which all the routes do, but LE24, meaning any route with a subnet mask less than or equal to 24. Router OSPF v3, 10, address family IPv4 unicast, and we're going to say distribute list, there we go, referencing the prefix list. Remember, you've got to put the word prefix or else it will assume that you're talking about an access list. And then we're going to say out EIGRP 100. So in this case, we're actually applying the distribute list not to the neighbor relationship, but to the redistribution process. All right. Now there's a couple ways that we can verify this. One of the ways we can verify this is we can come in and do a show IP prefix list, and put in the detail keyword. And we can see actually whether or not we're getting any hits on the prefix list. And we can see we're actually getting 2 hits on the prefix list. I didn't put in the sequence of 5. It automatically sequenced it for me. You don't have to put the sequence number when you're configuring the prefix list. So what is this matching? It's not matching what's being denied. It's matching what's being permitted. So that's going to be the 172.16.13 subnet with a /24 and the 172.16.21 subnet with a /24. All right. So if we go over to router 4 and we do a show IP route OSPF v3, we should see those routes. And sure enough, there's the 13 and there's the 21. All right. Very, very simple concept. Our last task is to do the same thing with redistribution for IPv6. We want to define 2 prefix lists. We'll just call this one EIGRP links. That's what they call it in the book. And we want to deny the 13:/64, but we want to permit everything else. So this is going to be a little bit different. And we're going to do this on router 1, of course, because that's our router doing the redistribution. So we're not necessarily, in this case, filtering on prefix length. We're just filtering a particular prefix. So config T IPv6 prefix list EIGRP links. We could probably name this EIGRP to OSPF as well, but that's okay. EIGRP links, and we're going to deny the 2001 DB8 0:13:/64 prefix. Remember, that's an exact match. You could still use the operators here. Just because it's IPv6 doesn't mean that we can't use the operators. All right. And then I would need to add a second line because there's an implicit deny at the end. I need to make sure that I'm allowing everything else. Whoops. And we're going to say permit :/0, which is basically any network, LE128, which is any mask. It's very equivalent to the quad 0/0 LE32 in IPv4. All right. In the opposite direction, for OSPF, we want to deny the 11 and the 12 subnets and then permit everything else. So IPv6 prefix list OSPF _ links, and we're going to say deny 2001:0:11:/64. We could use a summary here. Well, no, actually we can't because this is a prefix list, so it has to be an exact match. We're going to deny 12 as well, and then we're going to say permit, in this case, permit everything else, :/0 LE128. All right? Both of them have that statement because, again, we want to be able to allow all the other routes to be redistributed. The only remaining task then is to go ahead and apply this to our redistribution process. All right? So now we're going to go into R1, into the OSPF process. Just kind of do this in the right progression here. Router OSPF, since we did EIGRP prefix list first, we'll apply that first. 10. Address family IPv6, excuse me, unicast. We already did the v4. And distribute list, prefix list, EIGRP underscore links out of EIGRP 100. You have to specify the autonomous system number. All right. So again, we've already done the redistribution. We did that in the very first task in the exercise. Now we're applying this filter to that redistribution process. All right. So I can verify this. Show IPv6 prefix list detail. In this case, I can even reference if I want to kind of look at one specific entry. We should have a hit count of 4 because there are 4 prefixes that are being allowed and 1 is being denied. Right? Remember, we are denying, in our case, the 13 subnet, but we're allowing these other, the 21, the 22, the 23, and the 24. All right? So that's why we have a hit count of 4. So this sequence number has a hit count of 1. And by the way, the hit count is not anticipating what it would have. It's actually comparing the prefix list against what's actually being matched. So we can actually see this is an effective prefix list. It's actually matching exactly what we would expect it to match. So if I go to router 3 now, and I do a show IPv6 route, OSPF, I can see those 4 prefixes, 21, 22, 23, and 24. Okay? All right, those are the loopback interfaces that are being redistributed, but the 13 prefix is filtered by the redistribution process. So now let's go back to R1. Now we have to do the OSPF side, the OSPF links one. So we're going to go config T, router EIGRP Cisco, address family IPv6, unicast, you don't actually have to put that in, but that's okay, topology base, and distribute list, prefix list, OSPF underscore links out, and in this case, we're not doing it out of, the book doesn't want us to do it this way. We're not applying this distribute list to the redistribution process. We're applying the distribute list to the EIGRP adjacency, just like we did in v4. So we're going to say out of Ethernet 1, 0. All right. So R1 is still going to have all those in the topology, do show IPv6 EIGRP topology, and it's going to have all of those redistributed routes in the topology, right here, right here, right here, right here, right here. But when I go to router, well, actually, let's verify that the list is working first, just like we always have done. So we're going to do a show IPv6 prefix list detail OSPF links, and we should see the hit counts here. So hit count of 3 for the 11, that makes sense. Hit count of 3 for 12, and a hit count of 20 for the remaining routes, which makes sense. Okay, that's exactly what we should see. So if I go to router 2, and I do a show IPv6 route, EIGRP, I can see the EX routes. We should have 5 of them, 41, 42, 43, 44, and 192. All right, 11 and 12 are filtered. It's exactly what we would expect to see. All right, even though 11 and 12 exist in the topology database on router 1, there's 11, there's 12. 12 is connected, 11 is redistributed, but it's being filtered from going to router 2. All right, so that concludes that discovery. Next, we're going to talk about route maps, and we're going to see the power of route maps. Those are very, very useful. So we'll see you there. All right, so the next section we're going to talk about is route maps. Route maps with respect to filtering in this particular case, but route maps are actually used for all kinds of things. They're a very, very powerful tool to do things like route manipulation, policy-based routing, and of course filtering if we want to apply filters. But the powerful nature of a route map is the ability to not only match conditions based on certain criteria, but the ability to set variables and set options based on those conditions. And that's what makes them a really, really powerful tool that we can use in our arsenal for filtering as well. Very much like an access list, it's a sequence of actions or a sequence of events that are processed from the top down. As soon as there's a match within the route map clauses, and I call them clauses because it's not just a single line of events, it's a group of events, so different set and match conditions within a clause. But as soon as we match a particular event, as soon as we match a particular route map clause, we stop processing the route map. The lines themselves, or those clauses that I keep mentioning, those are going to be sequentially numbered, which allows us to identify the order of operations. The route maps are named. There is no such thing as a numbered route map. And then within the route map, we use if-then logic to identify the match criteria. If it matches X, then we do Y. And we do the Y by using a set condition. Within the matching statements, we also have the ability to do different kinds of Boolean matches. We can do a logical AND, meaning match this and this and this. And if you match this and this and this, then you can do this. Or we can do a Boolean OR, match this or this or this. And if you match this or this or this, then we do whatever the condition says. So it's a complex list, if you will, of these different match conditions tested against whatever we're matching against. And that's the other powerful thing about a route map, is that we have lots and lots of things we can match against. We can match against a prefix list, we can match against an access list, we can match against packet markings, we can match against where the packet is coming from, and so on. So because we can call out all these different match conditions, we have a whole lot of options with regard to what we can do with these particular route maps. All right? The collection of route map statements, in other words, a bunch of different route map clauses that have the same name, are considered the route map. So it's not just a single clause. It could be 3 or 4 or 5 or 6 different clauses. And then each of those clauses can be edited independently, but altogether, that is the entire route map. So the most important thing and the takeaway from this particular section, and we'll take a look at route maps with regard to our process in the next discovery, and I'll kind of expand a little bit on what the discovery includes to give you guys an idea about what these route maps can do. But we're going to take a look at the configuration. But within the scope of this particular section, it's important just to understand in general how the route maps are created and what are some of the rules for creating these route maps. All right, but like I said before, the statements in a route map, they're pretty much the same as an access list. We have specific match conditions, and then we have different set conditions. There is a big difference though, and the major difference between a route map and an access list is that access lists don't provide us the ability to do set conditions. All we can do with an access list is act as a classifier or a filter if we're doing an access list applied to some filtering scenario like a security ACL. In the context of a route map, we actually have the ability to do set conditions. All right. What are some of the common uses of these route maps? Like I said, we can use it as a filter for redistribution, and it's much more sophisticated than just simply applying a distribute list to a filtering process or to a redistribution process as a particular filter. And that's what the scope of the route maps in this particular section are related to. We can use it for policy-based routing. Policy-based routing gives us the ability to override our normal routing behavior. So let's say, for example, we have a routing table in our global rib. Our global rib is our routing table. And in that routing table, we have a default route for the internet traffic. And let's say that web traffic and FTP traffic and whatever other traffic matches that default route. And normally it would get routed over the next hop, over to the next hop, or over the exit interface that is defined by that default route. But what I can do is I can create a route map that matches a particular type of traffic. And we might do that matching of the traffic with an extended ACL that matches source and destination IP or source and destination port number and so on. And then I can say, set the next hop as an example. So what I'm doing is I'm overriding the default routing behavior, and I'm saying for this particular type of traffic, the next hop is not going to be what matches in the routing table. The next hop is going to be what's defined in the set statement in the route map clause. And that's what we define as policy-based routing. We're routing based on an administrative policy that we've configured on the platform and not based on what the normal routing procedure would be if the packet were left alone and the router could process the packet as a normal packet. So that's a very, very common implementation of a route map, is to do it for policy-based routing. Also very common is to apply route maps for BGP policy augmentation. If I want to implement a particular BGP policy, BGP policies, and we'll see this in our future discussion, but BGP is a path vector protocol, and it makes routing decisions based on path vector attributes like AS path and MED and weight and local preference and so on. And those attributes are actually settable attributes within a route map. So we can use a route map to match prefixes, match destinations, we can filter routes, we can change policy in BGP by setting different conditions of the route and so on. And so it's a very, very common tool in the context of BGP, these route maps themselves. All right? And the book kind of talks about this a little bit and filters it down to, based on what we're talking about here. All right, but take a look at this here. This is an important, kind of an important concept here that I want to point out. So let's say, first of all, it's a list of statements, right? And that's a really important concept. So if you're looking here, the route map operations we already talked about, right? It's a list of statements, what we call clauses. You look at the example, we can see clause 10, we can see clause 20, we can see clause 30. Those are arbitrary numbers that you decide to use, okay? Clause 10 just represents the order of operations. So 10 is going to be processed before 20, which is going to be processed before 30. Keep in mind, those numbers can be anything that you want them to be, but they do need to be listed in the order that you want the route map processed, because the route map is processed from the top down. So it's going to process clause 10 first, then clause 20, and then clause 30. You'll also notice the name of the route map. In this case, it's my route map. Each of the clauses has the same name, which indicates that it's part of the same overall route map. And then we have our actions. Is it going to be a permit or a deny? What it's permitting and what it's denying is going to be purely based on what is matching in the match statement. All right? And by the way, it also matters what the route map is applied to. Is it applied to redistribution? Is it applied to policy-based routing? Is it applied to BGP? So the permit or deny is going to really, the effect of the permit or deny, is going to really make a difference in specifically how the route map is applied. You have a series of match statements within the clause. You have a series of set statements. Now, you don't always have to use set statements. You don't always have to use match statements. All right. If, for example, I have a match rule, but I don't have a set rule, then the match condition is simply to match the permit or the deny of the route map clause. And maybe we're going to deny redistribution. So there's no need to always use the set condition. A clause does not have to have a set condition. The only time I would use a set condition is if, say, for example, I am redistributing, but I want to set the conditions of the redistribution. So maybe my match statement is matching network XYZ, and I'm permitting the redistribution because it's a permit clause, but then I'm setting the metric type, or I'm setting the default metric. Make sense? So match could just simply mean, let's just go ahead and permit the redistribution without setting any conditions. The set allows you to set conditions. And as the route map is processed from the top down, let's say, for example, the last clause, clause 30, is supposed to be your kind of catch-all clause. So we're not matching anything specifically. If you don't match something specifically within a route map, it matches everything that's left over. So if I've matched network XYZ in clause A, or the clause 10, and I've matched network ABC in clause 20, whatever's left over would match to clause 30 if I didn't have specific match conditions. Does that make sense? So just keep that in mind. And also keep in mind there's an implicit deny all at the end of the route map. Now, unlike an access list that's applied as a filter, the implicit deny all here doesn't mean necessarily that we're going to block traffic. It might block something happening to the traffic. For example, in a policy-based routing policy, the deny all at the end doesn't say, well, just don't route. Excuse me. The deny all at the end says just don't policy route. All right? So the effect of that implicit denial at the end is really going to depend on what it is that you are, how you're applying the route map in your environment. Okay? So every line has at least a permit or deny. Every clause is a permit or deny, and so on. Now the match statement itself, you have an option to do a logical or a logical and. They have that listed here, right? We search for the match conditions on a line-by-line basis. And this is really important right here. If the match conditions are identified in the same line, like this example, route map, my route map, permit 10, match IP address ACL1, ACL2, ACL3. In this case, I'm referencing 3 different access lists. Now clearly, maybe not so clearly, but should be clear, there's no way to match a single packet to 3 different access lists. All right, so when you have the match conditions listed sequentially in a single line, that is a logical OR statement. Match ACL1 or ACL2 or ACL3. So the packet's going to be compared against access list 1. If the packet doesn't match anything in access list 1, it's going to be matched against access list 2. If it doesn't match anything in access list 2, it's going to be matched against access list 3. And if it doesn't match anything against access list 3, then it doesn't match the clause. All right? So that means that the packet would be processed by the next clause in the route map. Just because a packet doesn't match the first clause doesn't mean we stop processing the packet. We will continue to process the packet down the route map until it matches a particular route map clause. In the end, there's always that implicit deny at the end of the route map. So if it doesn't match any of the previous clauses, then however the route map is applied will infer that that packet is going to be denied. Maybe it's redistribution, so we're not going to redistribute. Maybe it's policy-based routing, so we're not going to apply a policy, and so on. If you have the match conditions in sequential order in separate lines, this is a logical and, meaning that all 3 conditions have to be matched in order for us to match that particular clause. The packet would have to match some sort of rule in ACL1. It would also have to match the interface Fast Ethernet 00. And it would also have to match a metric of 3. All right? So that sequence is really, really specific and really unique. So obviously there's those 3 criteria would have to match in order for the packet to match that particular clause. All right? As I mentioned before, route maps can have multiple route map statements. The statements are processed from the top down, just like statements are processed in an access list. The first match that's found, the route for a particular route or for a particular packet, depending on how it's applied, that gets applied, and then that sequence number is used in the process. Okay? So you can already see, hopefully, just by our brief discussion here about how powerful these route maps can be. And we haven't even gotten into the discussion about the set statements, the ability to set criteria or even set multiple criteria. All right? So again, there is an implicit deny at the end of every route map. And the way we create a route map is we define the route map with a name, and that name is case sensitive. When we reference that route map in a policy, it is case sensitive. In this case, it's my route map. We specify our permit or deny statement, and we specify the clause number. Again, it doesn't really matter what that number is, as long as you define it sequentially. Could be 1, 2, 3, 4, 5, could be 100, 200, 300, 400. However you decide to do it. I generally like to go in increments of 10 because it keeps the list those numbers relatively small, and it still provides me the ability to add additional clauses in between later on if I want to. All right, so in this case, they're doing a match. They're matching the IP address of the packet or of the route. It, again, really depends on how the route map is applied based on prefix list my list, and then I'm setting the metric type to type 1. So this very most likely is probably some sort of route map applied to redistribution. All right? So consider these steps when you're setting up the route map. Set the conditions that you want to match. Define the action that you want to take, which could either be a permit or deny, or it could be a set action, and then apply the route map to the process that you're trying to manipulate. Could be redistribution, could be policy-based routing, could be BGP attribute propagation, and so on. All right? The sequence number is kind of basically identified for you. If you don't define one, then it's going to set it to 10, and then each consecutive entry would have an increment of 10. If you only have one entry defined with the tag, that becomes basically the default with the route map. The sequence number, in other words, gets decided for you. So you could theoretically, if you only have a single condition, you could just say route map by route map and hit return. It would imply a permit, and it would imply a sequence number. So you don't necessarily have to apply those. But again, if you're manipulating a route map post-configuration and you're adding entries or you're deleting entries, then having the appropriate number in that case would be important. You know, being able to identify the route map based on a particular number. Let's take a look at an example here. Oops, let me get rid of that. Take a look at an example here. So this is, again, the same kind of example that we saw before. We're taking routes from EIGRP and we're sending them into OSPF. We want to distribute 10, 11, and 12. So this is very similar to what we saw previously. Those two networks we want to be redistributed. These two networks we do not want to be redistributed. So we create a prefix list, just like we did before, that matches network 10 and 11. So that didn't change from our previous configuration. And then we go into our route map. In this case, our route map is called rm_into_OSPF. We're matching the prefix list that we previously defined. We're setting the metric to 25, and we're setting the metric type. Now, the route map doesn't actually know that we're going into OSPF. All right? These are generic terms to describe the metric. We could easily use a route map to set the metric for RIP. We could use a route map to set the metric for OSPF or EIGRP. The command is still the same. So the route map doesn't necessarily care if it's an OSPF route or an EIGRP route. But what if I was redistributing into EIGRP and I put these two commands in, set metric to 25 and set metric type? Basically, the route map would still function. Metric type just would simply not get applied because there is no metric type for EIGRP. Does that make sense? At least not a type 1 metric type. So you still want to pick your set conditions based on where the route map is being applied. You want to choose the appropriate set conditions, but the route map does not go back and say, okay, I'm applying this to redistribution into OSPF, so the route map is not considered valid anymore because it's using different set conditions than it should be using. It's just you have to make sure you configure it correctly from the start, okay? And then the last step, we're going into our OSPF v3 process and we're redistributing EIGRP into OSPF using route map RM into OSPF. So now we are redistributing only the two prefixes that were permitted. Remember, there's an implicit deny at the end of a prefix list as well. So because 13 and 14 were not explicitly permitted, they were implicitly denied. And then because we matched that address list, so this acted as a primary filter, and then this acted as a secondary filter to be able to set these conditions of the redistribution. All right? Really, really powerful tool. Really powerful tool. And then when we go back and look at our routes, we can see that the routes came in as OE2. We didn't, let me see here. That's probably the before, and this is the after, yeah. So this would have been the redistribution without the filters applied. All four routes got redistributed. They came in as E2 with a seed metric of 20, and then this is after the route map was applied. All right, E1, cost of 35, and which we didn't set. We could have set that value too. We could have set the initial seed metric just by putting in the word metric. And that's the nice thing about this. You can do multiple set conditions. I could have had another one that said, well, they did set it to 25. So we could have changed that to whatever number. Set the metric type, and then you use the set question mark in the syntax, and you can see all the different set options. When we do our exercise next, we'll talk about that, which does bring us to Discovery 13. We're going to now take a look at a practical application of manipulating redistribution using route maps. All right. All right, into Discovery 13, manipulating redistribution using route maps. And in this discovery, we're going to learn how to use route maps to manipulate redistribution. We've already learned how to do the redistribution. We've spent a lot of time talking about that. But we're also going to learn about how we can change administrative distance of routes to implement routing of IP traffic over the correct path. You can see from our topology here that we have a potential for suboptimal routing. We also have a potential for routing loops based on the fact that we're going to be doing two-way or mutual redistribution on 2 points in the topology. So the first thing we're going to do is we're going to configure redistribution between OSPF and EIGRP without using any filtering mechanisms at all. Then we're going to configure route maps to filter routes within the redistribution process. We're going to explore this process by using both access control lists and route tags to complete the filtering process. All right. We're also going to take a look at changing the administrative distance for certain routes so that we can enable optimal path selection or optimal routing path selection. So there's a lot of things we're going to be doing in this particular discovery. R1, R3, and R4 are configured with OSPF v3. for the v4 address family only, and R1 and R2 are configured for EIGRP for the named mode for v4 only. So we're not really running any IPv6 in this particular topology. All the devices are already configured. All right, so we have 4 major tasks that we're going to complete here. We're going to configure mutual redistribution between OSPF and EIGRP. We're going to apply route filtering using route maps and ACLs, and then we're going to apply a route filtering using route tags, which is a very graceful and easy way to filter redistribution. And then we're going to modify the administrative distance to avoid suboptimal routing. All right, namely when we redistribute into EIGRP, we're going to have AD values of 170, which would make the OSPF routes more preferred. All right, we'll see what the problem with that is. So again, my first task would be to go into R1 and to go into R4 and make sure that we have all the routes that we're supposed to have. In R1, we should have 1, 2, 3, 4, 5, 6, 7, 8, 9 OSPF routes and 5 EIGRP routes. So let's do a show IP route. We should have 9 OSPF routes. 1, 2, 3, 4, 5, 6, 7, 8, and 9. And we should have 5 EIGRP routes. 1, 2, 3, 4, and 5. I'm just basing that off of what's in the topology. Anything that's not connected needs to be learned. So R1 looks good. R4 should have 5 OSPF routes. And it should have 5 EIGRP routes. So let's go to R4 and make sure we have 5 OSPF and 5 EIGRP. So we have 1, 2, 3, 4, 5 OSPF routes, and 1, 2, 3, 4, 5 EIGRP routes. Okay, so thankfully in this particular case, we don't have any issues with the routing on our redistribution points. Now if I go to router 2 and I do a show IP route, just to kind of verify the initial state of router 2's routing table, looking at the topology diagram, router 2 really should not have any routes except for local and connected routes. Because even the EIGRP links to its peers are connected. So it should just have 1, 2, 3, 4, 5, 6 connected and 6 local routes. So let's go to router 2, show IP route, pipe, include local pipe connected, and we can see those routes 1, 2, 3, 4, 5, 6, and then we have 6 local routes as well. All right, so that looks good. Router 3, looking at the topology diagram again, router 3 should have 4 learned routes through OSPF, and it should have 6 connected routes. All right, so let's go to router 3 and verify that. Show IP route, pipe include, connected, pipe L, pipe O. And we have 1, 2, 3, 4, 5, 6 connected routes, 6 local routes, and there's the 4 OSPF routes. So everything looks good from that perspective. It looks like everything is okay. So now that we've verified all of our functional routing, we can start to add our enhanced routing features. The first thing is to do just basic two-way redistribution between OSPF and EIGRP on both router 1 and router 4. So let's start in router 1, and let's go into global config mode, router EIGRP Cisco, and address family IPv4 unicast autonomous system number 100. We're going to go into our topology base, and we're going to say redistribute OSPF v3 10 metric. And again, in this case, the numbers we pick here are not necessarily arbitrary. This is where we might have to be a little bit more creative on what metric we choose. Now, we are choosing kind of arbitrary values at this point because we want to see what the detrimental effect of mutual redistribution at 2 points in the network does. So we're not really looking at, okay, what would be the best path, what should be the seed metric, and so on. We're kind of basically just applying basic mutual redistribution. So router OSPF v3, 10, address family IPv4, unicast, and redistribute EIGRP 100. All right, do show run pipe section router. So we've got our redistribution in both directions on this router. In EIGRP, we're redistributing OSPF, and in OSPF, we're redistributing EIGRP. Okay? We'll do the same thing on router 4. All right, config T, router, EIGRP Cisco, and address family IPv4, unicast, autonomous system number 100, topology base, redistribution, OSPF v3, 10. Again, the metric, normally I would kind of consider what the metric should be, but we're just going to make it the same metric that we did for the other redistribution point. And then router OSPF v310, and we're going to say redistribute EIGRP 100 under the address family. So address family IPv4, unicast, redistribute EIGRP 100. All right? So we've got redistribution configured. Now we need to kind of go and verify the impact. Is it good? Is it bad? What's supposed to be happening? Now, if you look at the diagram, the other thing that I think is important to note is what we think should be happening. In our mind, understanding the topology, what should be happening. If R2, for example, wants to go to the loopbacks on R3, it makes sense that R2 should be going through R1 to get to those loopbacks. If R2 wants to go to the loopbacks on R4, it should go over the 21 link to get to the loopbacks on R4. Make sense? Even if R3 wants to go to the loopbacks on R4, R3 should be going through R2 and down to R4. That's interesting. This is a serial link, which means it's slow. And this Ethernet path is actually a better path for R3 to get to those networks. It's probably not what's happening, but again, that's the idea. We're now faced with kind of a complex scenario of routing. R4, for example, should go directly to R2 to get to these loopbacks. R3 should go directly to R1 to get to the loopbacks on R2. So that's what we have to kind of figure, what's happening in this particular case. Now, I will preface this discussion by saying that in IOSV, namely what we're running here in GNS3, I have seen some scenarios where the routing doesn't reflect what's supposed to actually be happening. And I'm not sure if it's a bug in the code or if it's a bug in GNS3, but let's see if we're faced with that. So show IP route, EIGRP on router 2. And what I'm looking for specifically are the routes that are being redistributed. And again, this is on router 2. Exactly what I suspected would happen is happening. It's load balancing. EIGRP looks at all of these networks, 10.1.0, 10.1.1, 10.1.2, 10.1.3, 4, 5, 6, and 7, as well as the 16.0 and 16.1 as equal cost paths. It's load balancing between R4 and R1. Why is that? Why is it load balancing between these prefixes? Any thoughts? Well, they're equal cost metrics, absolutely. But they're equal cost metrics because we applied the same seed metric in the redistribution process. So when we injected the routes from R1's perspective, it has the same metric. when we read that same metric as the metric that we use to inject in router 4. And the Ethernet links, of course, inside of EIGRP are going to have the same cost. So router 2 thinks that those networks are reachable the same way. So logically, how would I fix that problem? When I redistribute routes from R1, I would want to redistribute these 4 networks with a lower seed metric and these 4 networks with a higher seed metric on router 1. When I redistribute from router 4, I would want to redistribute these 4 networks with a lower seed metric and redistribute these 4 networks with a higher seed metric. So that R2 would think it's better to go to R1 for these 4 networks, and R2 would think it's better to go to R4 for these 4 networks. So that's a relatively simple solution. We just simply set up a route map. First of all, we set up prefix lists to match the appropriate prefixes. We set up a route map, and we use the route map to apply redistribution unequally in the process. But this is what I was talking about before. When you get faced with this complex scenario, you need to make sure that you're understanding logically how routing should occur, and you need to apply your redistribution to make that happen. All right? We didn't do that. We did mutual redistribution, and we injected the same seed metric. So now we're doing equal cost load balancing, or ECLB, to all of the networks in the OSPF domain. They all have a feasible distance of 107.5.200. All right? The issue is the serial link, of course. I don't want to, and in the case of EIGRP with load balancing, if I ping the 10.100 subnet, one packet is going to go this way, the other packet is going to go this way, one packet is going to go that way, the other packet is going to go that way. So that's definitely not something that we want. So we already know that we see a problem there. Let's look at router 3's perspective, how the EIGRP routes look in router 3. So we're going to go into router 3, and we're going to do a show IP route OSPF v3. And in this case, what we're seeing is that for the 10.2.0, the 10.2.1, the 10.2.2, the 10.2.3 network, we're going over to 0.2. Now, look at the diagram here. That's Ethernet 1.0. That makes sense. The 10.2.0, the 10.2.1, the 10.2.2, the 10.2.3, we're going over this link from router 3's perspective. All right? That actually kind of makes sense. But notice here that these are E2 routes, which means the cost is 20. So you might say, well, wait a minute. If the cost is 20, then why am I not load balancing? And this is where it gets a little bit interesting. This is a little bit beyond the scope of this particular exercise, but if I do a show IP OSPF database external, all right, do OSPF v3, external, we can see, actually let me do just the database itself to start with. We can see the type 5 LSAs. And I can see that I'm actually learning about those external LSAs, the redistributed routes, from both sources. I'm learning about them from router 1, and I'm learning about them from router 4. The same prefixes from each of those peers, which makes sense. Those are the routers doing the redistribution. But it's the type 4 LSAs, which are my right here. Nope. Where are they? These are my type 3s and my type 1s. Intra-area prefix link states. I believe that's them. Those are my type 9s. I should see some type 4s. Router net type 8. Remember what the type 4 LSAs represent, right? The type 4 LSAs represent the ASBR. But we're not going to see type 4s in this case. We don't need type 4s because we don't the ASBR is that we only have a single area. And a type 4 is only going to be generated into the area that the ASBR is not attached to. So we don't see type 4s here, but we will use our type 1s to reach those destinations. All right, notice the EBIT is set here, EBIT is set here, meaning that both router 1 and router 4 are injecting external routes. So if I do show IP OSPF database router, we can see router 1, right? It's an autonomous system boundary router, all right? And we can see router 4 as an autonomous system boundary router. But look here, link metric, where is it? Link metric, I gotta find it right here. So here's router 1, link metric is 10. So I know that this is a better ASBR than router 4 because the destination, the metric to reach that ASBR is 64 for router 4 as opposed to 10 for router 1. So in our case, in OSPF's case, because we do routing to nodes and not to networks, OSPF is smart enough to say, yes, I'm learning about both of these prefixes from the two different routers, the two different ASBRs, but I know from my type 1 LSA, it's easier to reach ASBR 1 than ASBR 4. We're not basing it on the metric of the route. We're basing it on the cost to reach the node. Does that make sense? Because if we were basing it on the metric to reach the route, then we would load balance because the seed metric for both of those is 20. So that kind of facilitates that whole idea that we route to nodes and not to networks in OSPF. All right? But there's another problem. There is another problem. In the case of, let me go back to, I mean, it's not a horrible problem, but it's definitely an inefficiency. If I go back and I look at the routing table, notice how I'm routing to 10.1.4, 10.1.5, 10.1.6, and 10.1.7. I'm routing via serial 2.0, which is an OSPF route. It's a route learned within my area. We already discussed that really I should go to router 1 to get to those networks. This is a bit of a harder problem to solve because it is based on how OSPF decides to route. OSPF will always trust an internal learned route, an intra-area route, a type 1 route, over a type 5. So even though I might be learning about 10.1.4, 10.1.5, 10.1.6, and 10.1.7 over through redistribution from router 1, so these networks are being redistributed into EIGRP, then they're coming up to R1, they're being redistributed into OSPF. OSPF is ignoring those because it trusts intra-area routes over external routes. So that is a bit of a more difficult problem to solve because I can't really change them from external to internal. There's no way to do that. It doesn't have anything to do with administrative distance because the administrative distance of E2 routes is 110, just like OSPF routes or intra-area routes. So it's a little bit of a more difficult problem to solve. We'll tackle that problem maybe a little bit later on. Okay? So how can I kind of manipulate this? There's a couple of ways that I can do this. Let's tackle the EIGRP problem first. The most graceful way, and frankly I think the appropriate way given that we are dealing with redistribution, would be to set up a prefix list to match these routes and then apply different seed metrics based on the routes themselves. So like I said before, on router 1, give these 4 a lower seed metric and give these 4 a higher seed metric. and then on router 4, give these a lower seed metric and give these a higher seed metric. That's certainly one way we can do it. The other way is we can just simply change how EIGRP sees the local interfaces. We can tell EIGRP this interface costs more or this interface costs more. But that's not going to necessarily work. Let's go ahead and do it and see what happens. So if I go to router 2 and I say config T interface Ethernet 10, we're modifying Ethernet 10, which is the link that goes to R4. And I'm going to set the delay value to something. The delay presently is well, actually, let's do a show interface Ethernet 10. The delay is presently 1,000 microseconds. So what I'm doing is I'm actually going to change the delay to 10 microseconds. It's entered in tens of microseconds, so 1 times 10. And if I do a show interface Ethernet 10 pipe include DLY, you can see now the delay is 10 microseconds. Okay? So that actually should make the path through R4 more preferred. But is it going to affect all of our routes, or is it only going to affect some of the routes? Let's take a look. Let's do a show IP route, EIGRP. Oops, do show IP route, EIGRP. And we can see here that it has affected all of our routes, which actually makes sense because all of the routes, we didn't change the seed metric. We still have the same seed metric in both directions. So all 8 routes are being redistributed at both points. We just simply made this link look much better, which solved the problem for 10.14, 10.15, 10.16, and 10.17, but it created the same problem now on the other side for 10.10, 10.11, 10.12, and 10.13. So now we're no longer load balancing, but now we're forcing EIGRP to send all of the traffic over Ethernet 10 for every one of the prefixes. So this is not the appropriate solution. All right? Definitely not the appropriate solution. So let's remove the delay value and let's do it the way we think we should do it, which is to use a route map and ACLs to match specific prefixes and then apply metrics based on those prefixes. So let's go no delay 1, set that back. Now if I do a show IP route EIGRP, I should see I'm load balancing again. And I'm going to go back to router 1. We'll do this on router 1 and router 4. And I'm going to start to configure an access list, access-list. And what I want to do is I want to create an access list to match the loopbacks on router 3, 10.10, 10.11, 10.12, and 10.13. And I want to create an access list to match the loopbacks on router 4, 10.14, 5, 6, and 7. So I'm going to call this R3 loop, IP access-list R3 loop. You could do this with, it needs to be a standard access list. You could do this with numbered ACLs as well, but I like to do this with named because then I can identify what the purpose of the ACL is. And I'm going to say permit. Now the R3 loops are 10.10, 10.11, 10.12, and 10.13. So that's a block of 4 starting at 0, 10.1.0.0, and it's a block of 4 starting at 0. So that would be a 0.0.3.255. So that's going to include 10.10, 10.11, 10.12, and 10.13. 10.10, 10.11, 10.12, and 10.13. And then I want to create another access list to match these 4 networks on router 4. So we're going to come back here, exit, and I'm going to say access list R4 loop. And I'm going to say permit 10.1.40 0.0.3.255. So that's going to be 4, 5, 6, and 7. You can create a block of 4 starting at 4 because 4 is divisible by 4. It's kind of an easy way to look at it. So I've created an access list on router 1, R3 loop, and R4 loop. We're going to do the same thing on router 4. Config T, IP access list standard, R3 underscore loop. Oops. And I'm going to say permit 10.1.0.0, 0.0.3.255, and IP access dash list standard R4 underscore loop, and permit 10.1.4.0, 0.0.3.255. All right, so now I've created the access list that's going to match those particular loopbacks. All right. Make sense? Now, I'm thinking here, hold on. Well, right now we're just trying to solve the problem in one direction. I was thinking if I wanted to go ahead and try and tackle the problem of the routes going in the other direction would be 10.2.0, 10.2.1, 10.2.2, and 10.2.3. So we would probably have to create some ACLs with R2 loop, but let's not do that just yet. Let's continue on by solving the problem in one direction, and then we'll focus on solving the problem in the other direction. The book kind of does it a little bit differently, but we're going to focus on one direction at a time. Now again, think about what the problem is. The problem is I want these loopbacks to look more preferred coming from router 1 than from router 4. And I want these loopbacks to be more preferred coming from router 4 than coming from router 1. I want router 2 to choose router 1 as the path to go here, and I want router 2 to choose this as the path to go here. So that means I'm going to have a route map. All right? So on router 4 and router 1, we're going to go ahead and create a route map. Route map, OSPF to EIGRP, permit 10, and we're going to say match IP address R3 underscore loop. Now, this is router 1. I want the redistribution to take place, OSPF into EIGRP, and I want to set the metric, but I want to set the metric to something more preferred. So maybe instead of 10,000, maybe it's something else. Now, this is what I kind of like to do in my scenario. We have an Ethernet 1.0 interface here, and we have a serial interface here. So I'm actually going to use the properties of this interface to set the seed metric. All right, so that should give me kind of an adequate value. So if I do show interface, Ethernet 1.0, pipe include delay, there's the bandwidth and the delay for that interface. So I'm going to say set metric. Notice the first thing we have is a value or bandwidth in kilobits per second, right? So it's actually telling us bandwidth in kilobits per second. And we're going to set the metric to 10,000, because that's what it is. And the delay is going to be in tens of microseconds. The delay is 1,000, so we're going to set it to 100 because it's in tens of microseconds. And then the remaining values I can just set to whatever. Reliability is 255, load is 1, and MTU is 1,500. All right, so do show run pipe section route map. we can see that we've got our first clause configured. OSPF to EIGRP. Now I'm going to create a second rule that says match IP address R4 underscore loop. And I'm going to say do show interface serial 20 pipe include delay. So those are the values for the serial interface. So I'm going to set the metric to 1544, a delay of 2000, a reliability of 255, load of 1, and an MTU of 1500. Make sense? That is going to make, for those loopbacks, that path less preferred. I would have to do the same thing on router 4 now. So there's an easy way to do that. But for router 4, I kind of want to do the opposite. For router 4, I want to make these preferred, and I want to make these less preferred. So I would actually use these values for router 4, and I would use the less preferred values for router 1. It doesn't quite match the diagram, but the point is to make one better or worse than the other. So I'm going to go to router 4. We've already done our access lists. And I'm going to say route map, get out of this mode, route map OSPF underscore 2 underscore EIGRP, permit 10, match IP address R4 underscore loop, and again, do show interface Ethernet 10 pipe include delay. Just to be consistent, set the metric to 10,000, 100, 255, 1, 1500, and then route map 20, and do show interface serial 20 pipe include delay, and set the match. We need to match our prefixes first. Match IP address R3 underscore loop, and then set the metric, and the bandwidth is going to be 1544. The delay is going to be 2000, 255, 1, 1500. You don't necessarily have to use the interfaces to do this. As long as one is preferred over the other, that's really all that matters. One has to be preferred over the other. So show run pipe section access dash list. Yeah, we can do that. And also route map. Oops, that's not going to show me everything. So we have our access list to match the loopbacks. Right here, we have a route map that says if it's an R4 loop, use this metric. If it's an R3 loop, use this metric as the seed metric. So the R4 loops are more preferred from this router and less preferred for R3. And then on router 1, do show run pipe section access dash list pipe route map. Okay, R3 loop, R4 loop, OSPF to EIGRP, match R3 loop. So the R3 loopbacks are more preferred and the R4 loopbacks are less preferred on this particular router. We're not done yet though, right? What's the last step? We have to apply the route map to the redistribution process. Show run pipe section EIGRP, because we're talking about OSPF into EIGRP. We're going to go into our EIGRP process. We're going to go into the autonomous system number, and we're going to go into the topology base. And we're going to say redistribute OSPF v3. We have to remove the old command first. Because if we don't remove the old command, it's going to leave in some of those values. So we're going to say redistribute OSPF v3 based on the OSPF to EIGRP route map. Okay. We'll do the same thing, so do show run section router. We're going to do the same thing with on the router 4. So OSPF to EIGRP, router 4, show run pipe section EIGRP, config T, router topology base, copy this line, take it out, and then put it back in based on route map. And this route map is also OSPF to EIGRP. And we should be done. We have applied a consistent configuration, easily readable, easily understandable, right? Because we used a naming convention that makes sense. Notice I also put all my names in uppercase so they stand out in the running config. I can see what's a name and what's a command, because commands are never entered in the running config in uppercase. So now let's see if the magic worked. We're going to go back to router 2 and look at our routing table. And sure enough, we look at this, half of the routes are going to Ethernet 1.1, loop back 10.1, 10.0, 10.1, 10.2, and 10.3 are being sent over to Ethernet 1.1, which is this way, and 10.1.4, 10.1.5, 10.1.6, and 10.1.7 are being sent over Ethernet 1.0. If I come into interface Ethernet 1.1 and I shut it down, notice everything is now going over the same interface. So very quick converge, because they were feasible successors. That's another thing to consider, by the way. When you're injecting that seed metric, that is the feasible distance or the reported distance for that destination. So you don't want the metrics to be so far away that they don't meet the feasibility condition, because then you have to send a query to learn the new path. But because they fell within the feasibility condition, let me do a no-shut and I'll show you real quick. Do show IP EIGRP topology. Let me make sure I get it after we've converged. Adjacency just came up, because I should see 2 entries for each of these. Eventually, I should see 2 entries. Interesting. Maybe I didn't do it with a feasible successor. Let me do a all-links. Nope, I didn't. Well, actually, let me see here. So we could probably tune this a little bit better. I think it converged quickly because it's just a small network and the query process didn't take that long. Let's see, 196, let's see, how many characters is this? 196, 608, 000, 173, 517, 595. Yeah, so these secondary routes do not meet the feasibility condition. So I need to change the seed metric, because I want this secondary route to meet the feasibility condition so that I don't have to do a query when the primary route fails. So rather than doing the metrics that I applied, I think I need to maybe change my route map, do show run pipe section route map, so that they're not that far apart and we meet the feasibility condition. So let's change, let's go into route map 20 and set the metric in this case. Let's just make it a little bit worse. Let's make it, instead of 1544, let's make it, I don't know, 8,000. And instead of a delay of 100, let's put a delay of 300. And then the rest will leave the same. This is an example, though, of understanding the protocol, understanding how it works, in trying to engineer a solution that's the most efficient solution possible. It did work. Our redistribution worked. Applying the different metrics to the redistributed routes worked just fine, no problem. But we ended up making EIGRP do more work because the secondary route didn't meet the feasibility condition. Show on pipe section route map. And I want to go into, in this case, clause 20. Oops, I forgot my config T. And I'm just going to copy the line from over here. Set the metric. So we're just making it a little bit worse, not a lot worse. So now if I go back to router 2, do I have feasible successors? Still I don't. Interesting. Still not there. It's closer. 196, 608, 800, 278, 528. So it's much, much closer than it was before, but it's still higher. This reported distance is still higher than the feasible distance of my primary route. So I'm going to play with this a little bit more. And I probably could just really just go like close, 9,200, which is just slightly worse than the other path, 2,000 microseconds and 9,000 kilobits a second. Now if I go to router 2, do I meet the feasibility condition? Gosh, I'm still not there. Let me check though. It is better because it was 2.7 before, now it's 2.0, but it's still just a little bit too much. Which actually makes sense. So we're going to just change the bandwidth. Bandwidth and delay have the same overall effect as far as the formula is concerned. They have the same weight in the formula. And let's see if that helps. Now we have a feasible successor. So the reported distance of this path is less than the feasible distance of my primary path. The overall feasible distance is still higher, but now it meets the feasibility condition, which means that if the primary path fails, my convergence is even more efficient because I don't have to send a query. This really does demonstrate this idea of engineering a network as opposed to just doing a config. Our original config worked. The original seed metrics that we chose, they were great. I mean, it accomplished our goal, right? Routes were going the right direction. But with our understanding of EIGRP and how EIGRP converges and the dual algorithm and whatnot, we realized that, hey, we need to maybe make this a little bit more efficient and not make the secondary path so bad that the path doesn't meet the feasibility condition. Make sense? So there's a right way of doing it and an easy way of doing it. We chose to do it the right way. So all said and done, if I do a show IP route, EIGRP, show IP route, EIGRP, we can still see that we're doing the right thing. 10.1.0, 10.1.1, 10.1.2, and 10.1.3 are going over Ethernet 1.1. And 10.1.4, 10.1.5, 10.1.6, and 10.1.7 are going over Ethernet 1.0. Okay? And if I shut down the interface, we're not going to get into the whole debugs and all that, but I mean, the convergence was practically instantaneous. Right? Everything is now going over Ethernet 1.0. Doing no shut, show IP EIGRP route. Coming back up, it took a little bit longer. Still converging. We still need to get the neighbor, but now it's back. So we have optimal routing for router 2. There is another problem though. We'll tackle that problem in a little bit. What about router 1? How should router 1 route to the loopbacks on router 4? Through router 2. How is router 1 going to route to the loopbacks on router 4? Through router 3. Because these are DEX routes, and they have an administrative distance of 170. But router 1 is also learning about those routes through router 4 with an administrative distance of 110. So that's another problem. We'll tackle that problem towards the end of our exercise. Router 1 should be going to router 2 to get to those loopbacks. Router 4 should be going to router 2 to get to the loopbacks up here. Same problem. Router 4 is going to choose the serial link because of the administrative distance. 110 is going to be preferred over 170. All right, so that's another problem that we're going to have to solve. We still have the problem, though, of the routes in the other direction. How does router 2 get to these loopbacks over here? Oh, we solved that problem, sorry. How does router 3 get to the loopbacks over here? How does router 3 get to the loopbacks over here? Okay. How do we solve that problem? Let's first investigate it. Router 3. If I go to router 3, and I say show IP route, pipe include E. So these are all the external routes. All right? Say E2, I guess. These are all the external routes. To get to 10.2.0, to get to 10.2.1, to get to 10.2.2 and 10.2.3, actually to get to all of them, it's choosing to go over Ethernet 1.0. There's 1, 2, 3, 4, 5, 6 routes. Well, that's kind of interesting too, because there should be, 6 makes sense. Because these 4 are connected. What I'm concerned about though, there should be 6, right? There's 4 here and 2 here. That's the 6 routes we're talking about. And it is choosing to go through Ethernet 1.0 to get there. All right, so router 3 is good. We didn't have to change anything in this respect. And that has to go back to our previous discussion about router 3 knows these routes are coming from R1 and R4. Right? Router 3 knows these routes are coming from R1 and R4, and it uses the cost to get to the ASBR to determine which is the better path. So OSPF is smart enough to figure that out, even though they're coming in as E2. And by the way, one of the things that I didn't mention as part of our discussion here is there's another way to verify if a route map is being effective. Just like we did a show prefix list, we can do a show route map. And it will show us what packets, how many packets are matching, or that'll show us at least, because this route map is being referenced in response to redistribution, we don't really see policy routing matches because we're not doing policy-based routing. But we can at least see the sequence that we have in place and what the clauses are for each of the route maps. All right, we don't get the hit count, but we do get to at least be able to see the route map itself. Okay. Now, we still have a bit of a problem. We know that router 3 is good because of how OSPF determines how to reach an ASBR. So router 3 is taking the appropriate path. But we do have a problem with router 1 and router 4. All right. Visually, and we're going to do this towards the end of our exercise here. I want to do another exercise real quick before we get into the next process. But visually, we can see that if router 1 wants to route to the loopbacks here, it should take the EIGRP path, which it really will, because EIGRP has an administrative distance of 90. OSPF has an administrative distance of 110. So even if router 1 is learning about those routes through router 4 through redistribution, it's still going to prefer the EIGRP path because it has a lower administrative distance. We're making that assumption, but it's the case. It's true. All right. What about R4? Same thing applies to R4. To get to those loopbacks, even though it might be learning about those loopbacks through redistribution from R1, it's going to use the EIGRP path. So in that direction, everything should be fine. All right. In fact, let's just verify it. Let's just go to R1 and do a show IP route 10200. Show IP route 10200. Oops. And we can see that it's known via EIGRP. It's redistributed, but it's going to 20.2, which is the Ethernet link 1.1. And that's this way. So it's interesting, it does actually show me that it's learning it through EIGRP, even though it's advertised by OSPF. So it's smart enough. So these are the two methods that it's learning it, but it's actually using the method of EIGRP. It's learning it through OSPF, but it's using EIGRP, and that has to do with administrative distance. We can assume that if it's that for that network, it's the same for the rest of the networks. And the same thing on R4, show IP route 10200. Same thing, known via EIGRP, even though I'm learning it through OSPF and EIGRP. It's advertised to my OSPF process, but I'm using the Ethernet 1.0 link, which is this link. So far we're checking all the boxes. Everything seems to be working correctly. The issue that we're going to see is how router 1 reaches these loopbacks and these loopbacks versus how router 4 reaches these loopbacks and these loopbacks in the OSPF domain. So let's do 10.100 and 10.140. Show IP route 10.100. So it says known via OSPF, which is good, and it's using Ethernet 1.0 to get there. That's good. That's actually great, because that means router 1 is using this link to get to those loopbacks. But now watch what happens when I do 10.1.4. Show IP route 10.140. It's learning it through EIGRP, but it's using the OSPF route, so it's going the same direction to get to router 4. And we already understand why that's the case. Agreed? It's the case because redistributed routes, external routes, well, actually, let me rephrase. R1 is learning about the 10.1.4 networks from R4 as a DEX route. DEX routes have an administrative distance of 170. OSPF routes have an administrative distance of 110. So the administrative distance in a tiebreak is always going to be preferred, the lowest number. So R1, and the same thing for R4. R4 is going to want to go to the serial link to get to these 10.1.0 subnets. So we know that that's the last, really kind of the last problem we have to solve with regard to, fixing the routing and so on. But before we do that, I want to introduce you to another concept, route filtering using route tags. And typically route filtering using route tags provides us the ability to manipulate two-way redistribution by applying a tag to routes that are being redistributed. Because ultimately what I want in my topology is I don't want routes being redistributed. I don't want R1 to redistribute these OSPF prefixes into EIGRP and then have R4 take those routes that were redistributed and redistribute them back into OSPF. Same in the other direction. I don't want R4 redistributing routes from EIGRP into OSPF and then R1 taking those routes and redistributing back into EIGRP. because that will introduce a routing loop or potential routing loop. May not happen. Specific criteria have to be met for that to occur, but there's a way to certainly prevent it from happening. And that's by applying route tags. It's a very simple concept. All right? These are labels that we apply to routes. And we apply these labels as we distribute. So in my redistribution process, not only am I going to set the metrics, I'm going to set labels so that when I do my redistribution, back I can match those labels and say, do not redistribute these routes that have these labels, redistribute the other routes. All right? So we can set and we can match the tags in our route maps. All right? So let's say, for example, we're going to tag the routes that come from R1 as with a tag of 1. We're going to tag the routes that come from R4 with a tag of 4. And then we can decide how to filter out or what to do with the filtering based on that. All right? So let's go back to our process. And I want to make sure I'm doing this correctly because I don't want to undo what we've already done. I want to apply this in addition to what we've already done. So let's start with router 1. All right. Show run pipe section route map. And I want to take all the routes from OSPF to EIGRP. And I want to tag them. We're also going to have to create a route map EIGRP to OSPF because we don't have that right now because we just applied the redistribution directly. So let's actually do that first since we haven't done that yet. So route map EIGRP _ to _ OSPF. So obviously this is going to be a way for us to identify all of the routes coming from EIGRP to OSPF. We didn't have to do anything special with setting metrics and metric types and all that. So that's not our goal here. Our goal is to set the tag. Okay? And if these are routes coming from EIGRP to OSPF, I'm just going to set a tag of 1. That's it. 1 permit clause. I'm not matching anything. If I don't specify a match explicitly, then match all is implied. So it's going to match everything that's being redistributed. That's it. That's the only thing I need to do. We'll change the OSPF to EIGRP in a little bit. This is EIGRP to OSPF. So do show run pipe section router. Actually, let's do section OSPF because that's what we're going to be modifying. And we're going to go into router OSPF address family, and we're going to say redistribute EIGRP based on route map EIGRP to OSPF. It's not going to change fundamentally how the redistribution is occurring, but it is going to apply a tag to those particular routes. All right, and I'll show you how we can verify that tag in a little bit. So that's router 1. On router 4, we're going to do the same thing. Config T, route map, EIGRP _ to _ OSPF permit 10, set tag, and in this case, we're going to set it to 4. That's an arbitrary number, by the way. I'm just picking 1 and 4 because those are the router numbers. So we can kind of identify where the traffic is coming from. In your real world, you might choose to use a different number. The tag number can be a pretty large value, anywhere from 0 to 4.2 billion. So you maybe can make it a building number or maybe based on an IP address or whatever. But that's it. So let's do a show run pipe section OSPF. And we're going to go into our OSPF configuration, and we're going to do based on route map EIGRP _ to _ OSPF. By the way, if you're doing redistribution and you reference a route map that doesn't exist, maybe you fat-fingered the name or something, redistribution will fail. So you need to make sure that you're referencing a route map that exists and that the name is correct. Okay? Let's see if it worked. If I go to router 3 and I do a show IP route 10.2.0.0, I should see the tag based on the route that I'm using. And sure enough, there's the tag of 1. If I shut down Ethernet 1.0 and I do a show IP route 10.2.0.0, as soon as we converge here, I should see it change. Did I change? I shut down the right interface. Why didn't it go away? No shut. Let me check my topology diagram. If I shut down this interface, I should not be learning that information from router 1. Yeah, I just didn't interface Ethernet 1.0. Maybe I was in the wrong interface. Shut down, do show IP route. There we go. That's what I should have seen before. 10.2.0.0. Yeah. So now it's a tag of 4. So this is also kind of an easy way to see where a route is coming from, even if you're not using it as a filter. So it's working so far. We're not done yet, because now we need to apply our filter in redistribution. So the objective here is to say, okay, I'm going to redistribute OSPF into EIGRP, but if the tag is 4, I'm not going to redistribute. And down here, I'm going to redistribute OSPF into EIGRP, but if the tag is 1, I'm not going to redistribute. Does that make sense? So we need to go to router 1, show route map, show run section route map, and I need to add a clause to router 1. Helps if you're in the right router. Show run pipe section route map. I need to add a clause to this route map that matches tag 4, but it needs to be a deny clause. So I'm going to do a route map OSPF to EIGRP. Oops, you got to do a config first, a connig first. And I'm going to say deny 5. So I'm actually adding a clause before the permit 10. I'm going to match tag 4, and that's it. It's already a deny clause, and the deny clause says deny redistribution. So anything that's tagged 4, which would be stuff that would have come in from router 4, that router 1 already knows about, by the way, because it's part of EIGRP, I'm not going to redistribute those routes because those were redistributed by router 4 into OSPF. Do show run pipe section route map, and we can see that there. All right? So we're denying the redistribution of anything that's matched, that is marked with a tag of 4. We'll do the same thing on router 4. Do show run pipe section route map. And we are going to go into route map OSPF to EIGRP, deny 5, match tag 1. So any route that is matched, that is tagged 1 is not going to get redistributed by router 4 into EIGRP. Because these were already routes that came from EIGRP. I don't want to send them back into EIGRP. We don't have to do it on the local router because the local router is never going to redistribute routes that it redistributed in the first place. It only redistributes routes that it learns from somebody else, not routes that it is already aware of. So that's why we kind of did that mirror configuration. Tag 4, tag 1, filter 4, filter 1. Now, it's not really going to affect our routing in this case. Our routing was clean enough that it didn't cause a problem. But this is just another precaution, just another configuration that protects possible routing loops. We need to do the same thing in the other direction. We need to do the same thing in EIGRP to OSPF. Well, we did it OSPF to EIGRP. We did the tagging. Show, hold on one second. Show run section route map. So we did the EIGRP to OSPF. We set the tag. We need to do the same thing in the other direction, OSPF to EIGRP. We also need to set a tag. So now we need to add another clause before 5 that permits everything and sets the tag. And then in this route map, EIGRP to OSPF, we need to add a clause that denies that tag. Does that make sense? So we tagged the routes coming out of EIGRP and OSPF, and we filtered them going back. We need now to tag the routes coming from OSPF into EIGRP and filter them going back. You have to do it in both directions. And we're not going to use the same tags in this case. I'm just going to use a 1-1 and a 4-4. You could probably use the same tags. Yeah, you could. You could use the same tags because it's applied to the redistribution process. The tag only gets applied if the route's being redistributed. So we can actually use the same tag values if we want. It might be a little confusing, so I'm going to use a 1-1 and a 4-4, but you could get away with using the same tag because the tag is being applied to the redistribution process. Config T, route map EIGRP to OSPF. We're going to do a permit. I'm sorry, the other one. We're doing route map OSPF to EIGRP. And we can actually use the same clause to set the tag. We don't have to create a separate clause. So set tag, and this is router 4, so I'm going to set it to 4-4. We have to do the same thing for the next statement as well. Set tag 4-4. So this is where we're actually doing the redistribution. So we're setting the tag to 44 for these routes. So we don't have to create a separate rule or a separate clause. We could have done that, but it would have prevented these other clauses from being processed. So we have to do it within the match conditions, within the match rules. We have to do the same thing on router 1. We're going to go into route map OSPF to EIGRP permit 10, and we're going to say set tag 1-1, and then route map OSPF to EIGRP permit 20, set tag 1-1, oops, set tag. And then we need to add an additional clause to EIGRP to OSPF, but this is going to be clause 5, and we're going to say, oops, it should not be a permit, it should be a deny. Deny 5. And we're going to say match tag 44. All right. We're on router 1. When I'm redistributing EIGRP back into OSPF, if something is tagged 44, I'm not going to redistribute it. And then the same thing on router 4, route map EIGRP to OSPF deny 5, match tag 1-1. Section route map. So let's see what's happening here. When I'm redistributing from OSPF into EIGRP, I'm setting a tag of 44. When I'm redistributing from EIGRP into OSPF, I'm denying that redistribution if it's tagged 1-1, meaning that it would have already been redistributed by router 1. For everything else that doesn't match tag 11, I'm going to redistribute it and tag it to 4. Does that make sense? So it gets a little bit confusing, right? Because there's a lot of things happening now, but this is the power of a route map. You get so much flexibility as to what you can do. When I'm redistributing from OSPF to EIGRP, remember I'm on router 4. I'm on router 4. Anything that's redistributed by router 4 is going to either be tagged 44 or 4. Anything that's being redistributed by router 1 is going to be tagged 11 or 1. So if it's tagged 11 or 1, that means it was already redistributed. There's no reason for router 4 to redistribute it again. And from router 1's perspective, if it's tagged 44 or 4, it means it was already redistributed by router 4 and it doesn't need to be redistributed again. And that's what's happening in this particular case. All right? OSPF to EIGRP. So if I'm taking routes from OSPF and I'm sending them into EIGRP, I'm going to deny the redistribution if the route is tagged at 1. So when I'm going from EIGRP to OSPF on router 1, I'm tagging it at 1. So this is saying don't redistribute them back into EIGRP if they're tagged 1. Otherwise, if they're not tagged 1, which would be the routes that are learned natively, meaning they're not tagged, then let's go ahead and redistribute them. These are the R4 loopbacks. We'll give them this metric. We're going to set the tag to 44. These are the R3 loopbacks. We're going to give them a worse metric. We're going to set the tag to 44. And that's it for that route map. So that's in the OSPF to EIGRP direction. In the EIGRP to OSPF direction, we're going to deny redistribution if the routes are matched, if the routes are tagged 11. If router 1 is redistributing from OSPF to EIGRP, it is tagging them 11, which means that I don't need to redistribute them. Otherwise, if it's not tagged 11, it's a native route in the protocol in EIGRP, and I'm going to go ahead and redistribute it, but I'm going to set the tag to 4. And we're doing the same thing on router 1. Do show run pipe section route map. We're doing the same thing on router 1. If it's OSPF to EIGRP, if it has a tag of 4, I'm not going to redistribute. Otherwise, I'm going to redistribute and set the tag to 11. If it's EIGRP to OSPF and it's tagged 44, I'm not going to redistribute. Otherwise, I'm going to redistribute and set it to 1. Make sense? This guarantees that we are not going to end up redistributing routes that another router had already redistributed. We still have a problem. We still have that whole administrative distance problem. This did not solve that problem. R1 still thinks it needs to go over OSPF to get to these loopbacks on R4 and vice versa. That has to do with an administrative distance problem. What we just applied is a filter to make sure that routes were not being redistributed back into the protocol. All right? So that's definitely something that we needed to fix. It didn't cause a problem initially. We went through and verified all of our routes, and the routes were good. From router 2, we know that router 2 should be using this path, the top path, to get to 10100. And that should have a tag of 1 or 11. I can't remember. That's where it's a little confusing. I can't remember if it's 1 or 11, but it should be 1 or 11. So if I go to router 2 and I do a show IP route 10100, it's tagged 11. So it's definitely coming from router 1. All right? If router 2 is going to these loopbacks, it should be tagged 44. All right, show IP route. (10.2.0.0). Oops, not 10.2.0.0. 10.2.1.0, I think. Hold on. Let me get the right route. 10.1.4.0. I wasn't even close. All right, 10.1.4.0. 10.1.4.0. And it is tagged 44. Okay? Conversely, if router 3 is going to the 10.2.0.0 subnet, it should be tagged 1. So let's go to router 3, 10.2.1.0, and sure enough, it's tagged 1. Which, by the way, tells me it's coming from 1. That's another benefit of doing tagging. Even if we're not using tagging for loop avoidance, it at least gives me a quick way of referencing where the route is being learned from and who's responsible for generating that route. If router 4 is going to the 10.2, it should just be using the EIGRP route. We'll just check that. I know that's the case, but we'll just check it anyway. Do show IP route, which should not be tagged, by the way. And it is using EIGRP. Okay? Notice here it does say it is learning it through redistribution. And it's learning it through redistribution based on redistribution applied to OSPF v3 using route map EIGRP to OSPF. But I'm not using that route. Now, if I were to shut down that link, if I was to shut down Ethernet 1.0, the route should show up with a tag. It should show up with a tag of 1. So interface Ethernet 1.0, shut it down, do show IP route 10.2.1.0, and sure enough, it shows up with a tag of 1 because we know now that it's coming from router 1. No shut, it's going to go back to the EIGRP route. Interface came up, got my adjacency. There we go. We're back to the EIGRP route. All right. But we still have that one problem to solve. And that one problem to solve is suboptimal routing. This, I think, is where GNS3 falls short, but we'll see if it works. I've updated my GNS3 since then. I've had problems with this working in the past, but the context and the syntax that we're going to use and the configuration options we're going to use should still apply. So we've got R1 and R4 that the last thing we need to solve. R4 should be using EIGRP to get to the loopbacks on R3, and R3 should be using EIGRP to get to the loopbacks on R4, right? And that's associated with administrative distance. The reason it's not happening is, again, because OSPF has a lower administrative distance than external EIGRP. And each router always looks at administrative distance if there's a tie, if it's the exact same prefix, and it considers which one to use when it's going to add a route to the routing table. Connected routes have an administrative distance of 0, static is 1, EIGRP summary routes are 5, external BGP is 20, internal EIGRP is 90, IGRP was obsolete is 100, OSPF is 110, ISIS is 115, RIP is 120, on-demand routing, we don't really ever talk about that, that's 160, external EIGRP is 170, that's what causes the problem here. IBGP is 200, and then unreachable is 255. Okay? So there's a couple of ways that we can do this. One way is to simply change the administrative distance of the protocol. So I can actually go into a router. In fact, I'll demonstrate this just as an example so you can see the syntax. I'm going to take it out after I'm done, but I could come into this router and I could say router EIGRP Cisco, address family IPv4 unicast autonomous system number 100, and I could go into my topology base and I could literally say distance EIGRP, set the internal distance and set the external distance. So I could literally go in and just simply change the administrative distance for external routes, making them more preferred or less preferred than some other route. And I could do the same thing in OSPF. I could go into OSPF and change the administrative distance of external routes, right? So I've actually kind of solved the problem a little bit, not really. R2, we've done this on R2 just as an example. It's not the right router to apply it to. But the problem with doing this is we're changing this for the entire global process. And we're only talking about 8 loopbacks, and the loopbacks are treated differently. So we can't really treat them as a whole by changing a global concept. We're going to have to manipulate administrative distance per grouping of loopbacks. So this doesn't really work in this scenario, changing the administrative distance of the protocol. All right, we could do the same thing in OSPF. If I came to router 3, for example, and I said config T router OSPF v3 10, oops, OSPF, and I go into address family IPv4 unicast, and I can say distance, and the case of OSPF, distance OSPF, I can say intra area, so that's my type 1s. I could set a value. I could say inter area, which is my type 3s, and set a value, and I could say external and set a value. So I can actually manipulate distance based on the type of route code. Is it an O route? Is it an OIA route? Is it an OE or ON route? Again, that applies to the whole routing process in this case. All right. So it's not necessarily the right solution in our particular case, again, because we need to treat those networks differently. If I did say router BGP 6500, we don't have BGP in this topology, but I might as well show you what it looks like. Distance is the command, and BGP, and I can set the distance for external BGP. I can set the distance for internal BGP, and I can set the distance for locally originated routes, routes that I'm originating. So even in BGP, we have the option of changing the administrative distance of the protocol. Again, that applies to the entire protocol. And that may be a solution. That may be a solution in this particular case. Well, not in this case. In some case, that might be the solution. But let's go to router 1, and let's confirm what our problem is. If I do a show IP route, and I look specifically at 10140. 10140. Now look at router 1. Router 1 is right here. 10140 is down here. Router 1 should go the EIGRP route to get to 10.1.4, but it is using the OSPF route. It's going over Ethernet 1.0. And we know why. Because of administrative distance. All right? Obviously, that makes sense because of administrative distance. So the 10.1.4 route is the loopback on router 4. R1 prefers the path over OSPF because it has an AD of 110. Even though that is a slower path, the serial link is slower, EIGRP just simply has a higher administrative distance, 170. All right? So let's just see if changing the administrative distance of the protocol solves this problem. I know it's not. It will solve half the problem, but it'll create another problem. But let's go ahead and do it anyway just to experiment. So I'm going to go into router 1. You can do this as well. I'm going to go into router EIGRP, Cisco, and I'm going to go into my address family for IPv4, unicast, autonomous system number 100, and I'm going to go into my topology base and say distance EIGRP 9100. Well, you know what's going to happen. The EIGRP route is now going to be preferred over the OSPF route because 100 is less than 110. Okay? So if I go to look at my routing table now, do show IP route, and I look at the 10.1.4, it is now going over Ethernet 1.1, router 1. Ethernet 1.1 is EIGRP. Great for that network. But also look what happened to 10.1.0.0. 10.1.0.0, it's choosing the OSPF route. Okay. We fixed that problem. And the reason we fixed that problem, actually, let me do something. Let me do a clear IP route star. I think this is where I started to see the issue. Yeah. This is where I started to see the issue. Notice it's now going over Ethernet 1.1, which it actually should be doing. I was going to say we fixed that issue with the route tags, but that doesn't have anything to do with it because router 1 is learning about the OSPF routes from two different sources. It's learning about the OSPF route directly from R4 through redistribution. Not re-redistribution, but the original redistribution. And it's learning about the 10.1.0.0 network through OSPF. What should have happened without clearing the route is it should have switched that route to the Ethernet 1.1 link because of the administrative distance. 100 is less than 110. It didn't do it automatically, and I think that's what I ran into the last time I did this. But we can see the problem. The problem is that we applied a sledgehammer solution to something that needs more of a kind of a finite solution. We need to manipulate the administrative distance of the routes independently. We only need to change the administrative distance of some of the routes, not all the routes. All right? So the problem now, the issue with this particular solution is that we prefer the path through R2 and R4 to reach the loopbacks that are even connected to R3. So there is a way to be more selective with the redistribution, with this change. So I'm going to take out I'm going to take out the distance EIGRP 9100. Again, this is the problem that I saw before. It should automatically switch back. It did. Okay, good. At least it did that. It switched back to the to the OSPF routes because again, now we're at 170 and 110 again. What I could do is I could say, you know what? I'm going to set the administrative distance for a specific route or for routes that I'm learning from a particular peer. All right? And if I recall correctly, I don't think this worked very well either, but I will at least show you the syntax. So I want to set the administrative distance of the routes that I'm learning from this peer. Let me think about this a second. This is the way it's supposed to work. We'll see if it works. All right? I'm going to go to router 1. And I'm going to create an access list, IP access dash list, standard. And I'm going to say this AD from _4. Thinking about this, I want to manipulate AD R4 _ loop. All right, so I'm going to manipulate the administrative distance for the routes that are, for the prefixes that are learned from R4, specifically the loopbacks that are learned from R4. And those are 10.10 or 10.14, 10.15, 10.16, 10.17. I could use the other ACL that I already created. Actually, you know what? I am going to do that. There's no reason to create another access list. I already have an access list that matches the loopbacks on R4. So let me get rid of that access list. We don't need it. It's just going to complicate things. If I do a show run pipe section access dash list, I can see that I already have an access list that matches R4 loop. So watch what I can do here. And this should work, but I don't know if it will. It should work in the real world. Again, I don't know if it does necessarily in our particular scenario. So router, EIGRP Cisco, address family, IPv4, unicast, autonomous system 100, topology base. And what I want to do now is I want to apply a different administrative distance to the routes that I'm learning from my peer, which in this case is router 2, but only the routes that are coming from R4. So what I'm going to do is, if I look at my do show IP EIGRP topology, not topology, neighbor, this is the peer, 172.16.20.2. That is the other router, router 2. So I'm going to say distance of 100. I'm going to set the administrative distance of 100 for all of the routes that I'm learning from my peer, as long as they are permitted by this access list, R4 loop. All right, it didn't like it. It should, maybe it needs a numbered ACL. Oh, I need the wildcard for the peer, 0.0.0.0. You could do this for like multiple peers as well. I'm doing it for a specific peer, and then I can reference the access list. So I'm saying, okay, take all the routes that I'm learning from that neighbor, which is 172.16.20.2, apply an administrative distance of 100 to the routes that are permitted by access list R4 loop. Do show IP route. And what should happen, which it didn't, I expected that to happen, this is what I saw the last time, is the 10.14, 10.15, 10.16, and 10.17 should have an administrative distance of 100 applied, and these should have remained at 110. So let me do a clear IP route star and see if it actually fixes it. It did not. That is definitely the way it's supposed to work. And I remember running into this situation before as well. But there must be another explanation here. You know what? I'm remembering now. Setting the administrative distance in this mode doesn't work for external EIGRP. That's why it's not being applied. So I guess the only other way to solve this problem, let's see if it works in the other direction. I think it's an external EIGRP problem. Let's see if it works in the other direction. I want to set the administrative distance. Well, see, I wonder if I could do it higher. R4 is preferring this serial link to get to 10.10, 10.11, 10.12, and 10.13. R4 is preferring the serial link because the administrative distance of those is 110. But if I make them like 180, then R4 should prefer this other link. So let's try that on R4. That'll confirm whether or not this is a DEX problem or whether it's a GNS3 problem. So let's do that here. We're going to go to do show run pipe section router. And we're going to go into our OSPF v3 address family. And we're going to go into our address family v4. And we're going to say distance OSPF. And then we're going to set the, we're only going to set the intra area routes. We're going to set the intra area because, again, I'm trying to make the DEX route more preferred for these loopbacks than the OSPF route. So it's the intra area, the O routes, and I'm going to set an administrative distance of those to 180. So 180 based on inter area will leave the same, 110, and external will leave the same. See, it doesn't allow me to apply an access list in this case. I was going to see if it would let me do it on the OSPF side, but this one, OSPF doesn't allow me to apply a filter to the neighbor. So this is a bit of a more of a challenging proposition. And we can't modify metrics because administrative distance comes into play before metrics are ever even considered. So we would have to probably use distribute lists. The problem with a distribute list is if you're using a distribute list, you wouldn't get any failover. I could go into router 4 and say, don't distribute R3's loopbacks over to R2. You know, I could filter out those loopbacks from being advertised. But if the link over here failed, then R2 should be able to go that way to get there. So then we would have to get into maybe doing some floating static routes with IPSLA and so on. That's a little bit beyond the scope of what we're doing here. So it's not an easy problem to solve because we can't do that distance based on a peer in OSPF. And I believe that applying distance to external routes in EIGRP is not permitted either. So that makes our life a little bit more difficult. But there's always a solution. There's always a solution. It's just a matter of how complex that solution is. But we'll go ahead and wrap up this exercise. You do at least know how you can apply distance in certain scenarios. Obviously, it didn't work in this particular case. But there is another solution for this as well. It's just kind of beyond the scope of what we're doing. So we'll wrap up this discovery. We'll see you guys in the next section. So we'll just wrap up this whole section here with one last brief section here. What are the caveats of redistribution? We've already seen from just our previous example, and that was a relatively simple network. It just happened that we were doing redistribution in two different directions, that it can get rather complex. The challenges that we run into are routing loops, incompatible routing information, meaning metrics they're not compatible with each other, suboptimal routing, inconsistent convergence times, different routing protocols deal with topology changes differently. So how do we fix these problems? We can use distribute lists, we can use route maps, we can manipulate metrics, we can manipulate administrative distance, and so on. So I think really kind of the most important takeaway from this is that there are a whole bunch of different tools that have to be used in order for us to be able to solve these particular problems. And you have to kind of pick away at them at layers. That's what we did in the exercise. We solved one problem at a time and kind of built on that, because you saw at the end we had a relatively complex configuration that if you tried to just kind of think of the whole thing at once and solve every problem at once, it would be really, really difficult. So there is a progression here. Before you do redistribution, make sure you have all your routes. Make sure that the routing exists on the 2 redistribution points. Make sure that the destinations exist. You might even check about the perimeter devices or the internal devices to the ASs, how they're routing. Do your redistribution. You know, obviously if this is a production environment, you have to be wary of that, but do the redistribution using basic redistribution. Again, go and confirm how the routing is working, and then try and solve each routing problem independently. So you go to maybe the EIGRP router, and oh, it's not choosing the right path. How should it be choosing the path? And then that's when you can manipulate seed metrics like we did. Make sure you put your tags in so you're not creating a routing loop, those kind of things, all right? So, but what was the most powerful tool that we had available to us to accomplish all this? It was a route map. The route map provided us the most powerful tool to be able to handle this. And that was really a critical piece to this. Being able to match and set all those conditions in the route map, and then referencing that route map from the redistribution process really solved a lot of our problems. All right? So that's the end of section 7. We'll just go ahead and move on into section 8.